Hey everyone, we're just getting set up in the meantime to get familiar with kind of the Zoom layout. If you have questions for the panelists, ask them via the Q&A tool, and we'll be keeping an eye on that and answering throughout. And then if there's anything that you think other attendees could help with the chat, you can send that to the chat to all panelists and attendees. And then we'll get going in a couple minutes. David, just let me know when you're ready. David is showing the GitHub repo, which we'll be working from on the shared screen. There's also a link to it in the Zoom chat. So if you want to go ahead and look at that and clone that to your preferred working space, that's probably a good thing to start with. No link in the chat. Oh no. By default, all attendees' audio and video is off. We can take you off of mute to ask a question if you raise your hand.
Okay, let's wait another couple of minutes and then we'll get started, everybody. So I'm sharing the the web page for the repository for this workshop so that you can download the materials by going to this green code button. So it's on github.com and then dp_sanders/learnjulia2020. Go to this green code button that I've highlighted, and you can either clone the repository if you know Git, or you can just download the zip file and just put it somewhere on your computer. And in that repository, if you scroll down in the screen, you'll see that there are installation instructions. Okay, are we ready, Mary?
I think so. Let's get started.
Okay, great. Okay, so I'm gonna actually stop sharing my screen for a minute. Start my video. Yeah, okay. Hi, everybody. Good morning, or afternoon, or good evening, or good middle of the night, depending on where you are in the world. I'm very happy to be here. Welcome to JuliaCon. First of all, welcome to JuliaCon 2020. So JuliaCon is the annual conference about the Julia programming language. And I was supposed to be in Portugal this year, but due to the current epidemic, COVID-19 epidemic, of course, that was not possible, which is a shame, but it gives us a great opportunity to welcome people from all over the world. Many people, in fact, there are thousands of people now registered for this conference. So it's an order of magnitude bigger than last year, which was the previous biggest one. And I believe, if I counted correctly, that this is the 7th JuliaCon. So the first one was in 2014, and there's been one every year since. This is the number 7. And so it's starting today. So there are 2 simultaneous workshops, this one on learning Julia via epidemic modeling, and another one on binary builder, which is a package to make using binary dependencies of your software easier. And so there'll be 2 workshops every day from now until Tuesday, and then the main conference, the talks, start on Wednesday and go through to Friday. So it's a fantastic opportunity to get to know something about this amazing language that we're all excited about. And so part of the goal of today's workshop is to try and show, try and give a flavor of why Julia is so, exciting, and why people are starting to realize that it's an excellent tool to use for all kinds of programming needs. Okay, so of course I'd like to thank the organizers of JuliaCon for giving me the opportunity to present this workshop. And it's a workshop about learning Julia, but it's not from the very, it's not a totally introductory workshop. I'm going to assume that you already know the basics of Julia. So basically how to use variables and functions and for loops and one-dimensional arrays or vectors, which I forgot to add, sorry, to the instructions. But actually I'll go over those quickly at the start anyway. So in particular, if you're coming from some other programming language, it will be hopefully, easy to pick up as we go along. Okay, so I'm happy to have Mary McGrath helping today. She's going to be monitoring Mary's going to be monitoring the chat. And yeah, so there's a chat and there's Q&A. So the Q&A is really about questions about the, about things that we're covering in the workshop. And in the Q&A, if you're following on Zoom, then please use the Q&A button to ask questions, and then you can vote on other people's questions and I'll cover the questions in order of priority, basically, given how many votes they have. And there's also a chat where you can ask questions to other attendees, and they'll hopefully help you if you're having trouble with something. There's also a live stream at the same time on YouTube. So if you missed something and you need to go back, you can actually do that on YouTube. Okay, you can't do that in Zoom, but you can do it on YouTube. So please, if there are any questions, just do use the chat, do use the Q&A in particular, and we'll try and answer the questions that you have. So there's already a question, which is the content of this workshop the same as the course on computational modeling in Julia with applications to the COVID-19 pandemic? So this is a course that we taught at MIT last semester during the lockdown, and it's available at JuliaAcademy.com, which is the Julia training platform. It's also available on YouTube on the Julia Lang channel. And the answer is that the material is very similar, yes. So this is a reduced version. I've changed some of the approaches, actually. Yeah, so there's some additional information in today's session. Okay. So if you already have Julia 1.2 installed, that should be fine, I think. Okay. So, I said a minute ago that there's a repository for this course. So here it is. So it's on github.com. This is actually linked from the information about the workshop on the JuliaCon page. There's a link to this. So it's github.com/dpsanders/learnjulia2020. And then you go to this green code button, and you can either clone the repository using Git, or you can just download a zip file with all the files in and unzip it. Put it somewhere on your machine. And then in this repository, there are the instructions to how to set up. So you want to install Julia. If you haven't got it installed, you need to copy and paste these commands to add the 3 packages that we'll use today. And then you can use these commands to run the Jupyter notebook, which is the environment that I've used to write the materials. So when you do all of these commands, you don't have to use the notebook. If you don't like using the notebook, or you don't want to install it or whatever, you can view the notebooks online down here at this NB viewer link. So just open that link and you should see that you have the notebooks there, and you can open those and just see them there. You won't be able to actually interact with the notebooks there. But you can just once you've installed Julia, you can actually just open a Julia terminal window.
Hey, David, are you, yep. We're not seeing anything right now.
Oh.
Do you want to share your screen?
Yeah, I'm sorry. You're right. I didn't share my screen. Okay, now can you see my screen?
Yes.
Okay, great, thanks. Okay. Yeah, so now, here is the repository, github.com/dpsanders/learnjulia2020. You go to this green code button, you hit the green code button, and you can either clone the repository using Git or just download the zip file. If you scroll down, you'll see the instructions. So you can install the latest release of Julia if you don't have it. Hopefully you all have already installed Julia. And then just copy and paste these commands to install the 3 packages that we'll need. So iJulia is an interface to the Jupyter notebook. And then we'll use these 2 Julia packages, plot and interact. And then once those have finished installing, they'll install some other packages and they'll tell you what they're doing. Then you just do using iJulia. Be careful with these. You have to get the right uppercase and lowercase. So it's capital I, capital J, and lowercase everywhere else. All package names start with capital letters, and then launch the notebook like this. So I'll just show you how to do that. So I'll just open a terminal. So once you install Julia, you can just run Julia by double clicking on the icon or various other ways to run Julia. I'm sorry about the there's somebody doing some kind of building work around my house. Sorry about that. Okay, so once we're in Julia, what can we do? We'll do using iJulia with capital I and capital J. That will load in this package called iJulia, which is like interactive Julia. And then we'll type notebook with parentheses, and that will actually launch this Jupyter notebook. So this, when we install iJulia, it will ask you if you want to install the Jupyter notebook. I recommend that you say yes, even if you have it installed, but you can say no, and then it will use, it will try and use a previous installation that you have. Okay, and you should see this window. So basically, Jupyter is a web application that runs inside your browser. So I'm actually in Chrome looking at this web page, and this web page is basically a browser, like a file browser for your computer. So you just need to go and find wherever inside your computer you just saved those files, the files for from the repository that contain the notebooks. You just need to sort of go in and go into, find whichever folder you put them in and go over there. And then, so you should end up with this view. So this is inside, some part of my computer where I stored these notebook files. So the notebook files end with this ending .ipynb, IPython notebook, even though they're not restricted to Python. That's what the name means. And then when you click on this number 1 introduction, you should see this. And now this is, if this is running on your computer, it's actually a notebook that you can interact with. And so, so there's this toolbar which you can use to, for example, add a cell by clicking this plus button here. It will add a cell, and then you can type something like x = 3. Shift enter will run the cell. Or you can use this run button up here on the toolbar. And then you can also use keyboard shortcuts. So in help keyboard shortcuts, there are all kinds of keyboard shortcuts. For example, escape A also adds a cell above the one you're currently in. Okay, so I think that's basically what you need to know to be able to interact with this Jupyter notebook. And you can also delete a cell with escape DD. And there are various menus up here that you can use. So I'm going to be using Julia 1.4.2. This is, excuse me, this is the latest stable release. Version 1.5 is about to be released very shortly, hopefully. Okay, any questions so far? I'll just take 2 minutes to let everybody try and reach this position, try and get to a stage where you can actually use these tools. So if for some reason your installation is not working, as I said, you can go to the notebook viewer that I showed, and then you can view the notebook materials. But the notebook materials do not have the results in of running the code. They have some pieces of code, and then they don't currently have the results in. So I'll be running the code live. And then there are some exercises which I'm going to ask you to do. Right, so this is a workshop, tutorial workshop. It's not just a lecture. And so the point is to actually get you coding. The only way you can learn, so in notebook viewer, these numbers don't come out right. This is supposed to be 1, 2, 3, 4, 5. Never mind. So it's supposed to be you getting hands-on coding Julia. That's the only way you can actually really learn Julia. Okay, so if you're unable to use the Jupyter Notebook on your machine, one solution is to actually go to this website, repl.it, repl.it.
David, could you post these links to the chat as well, so that people can quickly click and go?
Right. Chat, where is the chat? Sorry. Yeah, there we go. Great, thanks. So repl.it, what it does is just press start coding, and you type in Julia where it asks for a language, and then create REPL. So REPL means read eval print loop. So it's this loop that's asking for input, and x equals 3. And then what is the value of x? It's 3. And so you can also type here some piece of code that you want to run. X equals 3. What is 2x? 2 times x. Run that, and it will run that code that I just typed over here. And no, it won't. Why didn't it work? Anyway, yeah, okay, so I haven't used it much, so I'm not sure it's supposed to. Maybe I need print there. Print line this. Yeah, there we go. So there's the answer from running my code. Okay, so those are some options. Okay, so I'm hoping that everybody has got everything set up, and I'm going to start the actual workshop. So the idea of this workshop is, as I was saying, to learn Julia, but learn Julia beyond the basics. So the basics are I'm going to use variables, I'm going to use functions, I'm going to store some data, going to generate some data in vectors, and I'm going to use that to do for example, to do some kind of simulation. So today we'll be simulating. So the whole workshop will be based around the idea of modeling an epidemic. Okay, so I want to show you actually the goal of today's workshop is to produce this visualization. So I don't know if we'll actually get all the way to the goal, but that's the end goal. So here we have some. Can you see this? Is it clear? So we have people. Most people are just walking around, going around this space, but one person is infected. This red dot here is infected, and so we'll actually be able to simulate the time evolution of. You see that as the red dots hit the blue dots, they'll infect them with some probability, and as time moves on, this infection will spread out, and then at some point people will start to recover and become green. And so you can see that we're making this sort of GUI as graphical user interface, where we can visualize the state of the system and at the same time visualize the dynamics of how many people are in each of these states. So the goal of the workshop is to be able to produce this visualization from scratch. So we're going to program everything ourselves, and it's a bit ambitious. But actually, the goal is really to understand how to use types in Julia to do this. So types are something that usually in a first course in Julia, I wouldn't mention very much, because you can write a lot of great Julia code that's avoids mentioning types at all. And it can be high performance. So that, the great thing about the Julia language is that it is both interactive and high performance at the same time. This is basically unique among programming languages. And so that means it solves the two-language problem. You don't have to mix a high-level language like Python with a low-level language like C++ anymore. You can do everything with one single language, which is Julia. So yeah, so the idea is that these, what I'll think of a person as, so this is an example of what we call an agent-based model, a model based on these agents. So an agent is something that has some kind of internal state. So in this case, the state of the agent is where does it live in space and what current infection status does it have? Is it infected or is it recovered? So we want to be able to create something called an agent that has that information inside it and then tell the agents how to move around and how to interact with each other. And that's the goal of today's workshop, to see how to do that in Julia. And Julia has a very unique approach actually to the way that it deals with functions and types. Okay. So there's a lot of text here that just says basically what I just said. So, okay. So we're going to start off by remembering some basic syntax of Julia. And we'll start off by flipping a coin. And that coin will model how people recover from an infection. So we have a person who just got infected, and we want to know when will this person recover. So the model that we'll use is that at each step, so we'll have time steps like days. So each day we'll say the person is going to recover with this probability on this day. So we'll fix the probability as something which is a value called P. And so it's like flipping a coin, but the coin is weighted so that it's going to fall on one side with a higher probability, a higher frequency. You can think of probability as frequency. So with probability P, the coin will fall on heads, and with probability 1 minus P, it'll fall on tails. This is what's called a Bernoulli trial. And there's a link to the Wikipedia page. So in Julia, we want to put everything inside a function. So here's a function to simulate a coin, right? So I'm going to type, let me just type that out again, actually. So, okay, so I'm going to start with the word function and then the name of the function. And then I have to put parentheses, even if I don't pass in anything to the function, any parameters, but I'm going to pass in one parameter, which is called P. And then I'm going to use this function called rand. So what does rand do? So if I just type rand, let me just move all of that out of the way. If I just type rand, it tells me that rand is a function and that rand has 69 methods. Okay, so this is the part that's pretty unique to Julia. Each function has lots of different methods or versions. And I can actually see all of those methods with the function called methods. Okay, so it's quite complicated. Let's not look at that right now, but those methods are different ways that we can use this function. But the simplest way we can use it is by calling it with no arguments. So if I call it with no arguments, I have to put the parentheses, because if I don't put the parentheses, it just tells me that this is the function. So when I put the parentheses, it gives me a random number uniformly distributed between 0 and 1. Okay, and then if I use Control Enter, I can rerun that same cell over and over again. So if I rerun that cell, I'll get a different random number. I run it again, I get a different number, etc. So this is how we're going to produce randomness in our simulation, or stochasticity. Okay, so if I do r equals rand, parentheses, then I'm actually defining a variable called r. So, we don't need to say what type r is. Julia will actually work out for us what the type is of r. And I can find that out with type of, which is a function. I give it the name r, and it tells me that it's a float 64, so a floating point number with 64 bits of precision. Okay. So I'm going to put r equals rand, and then what I want to do to generate, what I'm trying to do is generate something with probability p. And so I can do that by just doing this check r is less than p, and then I'll finish the function. and I want to actually return that result. Okay, so when I do Shift Enter, it evaluates this definition and tells me, oh, you just generated a new function called coin. Okay, so let's just look at that. So I've got my random number that I generated outside the function, and then I have, for example, 0.3. And so what happens when I ask Julia, what is r less than 0.3? And the answer is that what it does is it says that it's true. So this is a Boolean expression that evaluates to either true or false. And Julia will return that value to us, and we actually see that result displayed. So in other languages, you often need to use print to print things out. In Julia, you almost never need print because it's always telling you what the result is, right? So even if I'm in the terminal, in the REPL, if I do, r equals rand, it tells me what the output is without me, needing to explicitly print it out. Okay. So what does this function do? So it generates a random number, and it uses that to return true or false with a certain probability, right? So how do I run that function? Well, I pass in the probability that I want to use. So here I've put it in 1/3. I'm passing it in to this function. So let me just write that out. Coin, I'm passing in, say, 1.3 or 0.25. Or even I can use a fraction with // So 1/3 / makes a rational number, which is a fraction. Okay, and it returns this true or false value. So if I run this a lot of times, I can see that different falses and trues are coming out. Okay. So we've made why did we put this in a function? Because we want to call it many times. So functions are for making pieces of code that are reusable, that I can reuse again and again. So the other syntax that we can use in Julia to write a function, if it's short enough, is this one. So this is called a short form or assignment form of the function definition. So we have coin, we pass in, it has one parameter p, and then we use equals to actually define the function. And then you can see that I squashed down all of that function definition that I wrote upstairs. I squashed that all down. And so I'm just going to go to full screen here. And so I can just write this all in one single line. So I no longer make my intermediate variable r. I just call this rand function, and then I check, is that less than p? That returns my Boolean value, and that's how I define my coin function. And we just should check that it actually does the right thing, and it does. Okay. So for those who joined late, Mary is helping out with the text, with the chat and the Q&A. So do use the Q&A button to ask questions. And every now and again, either Mary will, answer there, or we will present the answer live. So let me just ask Mary if there are any questions I should answer right now.
No open questions. There are a couple of people with their hands up. If those people still have questions, I can take them off mute briefly. Is that okay, David?
Sure.
All right.
Yeah, so everything is being recorded. So, just if you don't want your voice recorded, don't ask a question with.
Charlie, you should be allowed to talk now. But you are muted. All right. Anirudh? They took their hand down.
Okay, let me carry on then. Okay. Okay, so what do we want to do with this coin flip? So basically we have this person who is infected, and at every day we're going to ask, on that day, does the person recover? And so the answer might be no on the first day, no on the second day, no on the third day. So every day we're flipping this coin to see if the person recovers. So here's an exercise for you. So run coin 100 times and store the results in a vector. So probably we should just remember how that works. So so how do I make a vector in Julia? Well, one of the ways is like this. So I can make, I just write open square bracket, close square bracket. That makes an empty vector, an empty one-dimensional array. So you can see that this is an array with one dimension, and it can contain anything. So I can put any kind of object in there. But it turns out that in Julia, we usually want to make, we usually do want to think about types a bit. So what I actually want to do is, since I know that these results will be, well, they're actually going to be Booleans, but I can make them into integers. So I'll store them in an empty integer array, right? So this is an array which can only hold integers. So I just wrote the name of the type int64 with a capital I in front of these square brackets, and that makes an empty integer array. And then I can actually add an element to V with this function called push bang. This bang or exclamation mark is an indication that I'm going to be modifying this argument V. Right? So V is an empty array, and I'm going to add something to it. So let's add the number 1 to it. Then that's how you add things to a vector. Okay, so I'd like you to do this exercise. So run coin a few times and store the results in a vector. And I'm asking you to think of 2 different ways to do this in Julia, if you know, another way to do it. And then you have to put that code inside a function, because everything needs to be inside a function in Julia, basically, because we always are going to want to reuse the code, and because that actually makes it more efficient. It runs faster if it's inside a function for technical reasons. And as I said, don't print things out, just return results. And then you can read the exercise, but make a function success rate that calculates the proportion of times that we were successful, and run it 1,000 times. And then we're going to use this interact.jl package to make this into an interactive visualization. So I'll give you something like 5 minutes to try and do this exercise, and then I'll go over some of it live.
Awesome. And David, we have some questions coming in the Q&A.
Sure.
About what? I'll read them to you. So one is, does specifying the type of the variable increase the speed at which Julia will run?
That's a good question. So there isn't really a way of specifying the type of a variable. So in general, the speed of Julia, the speed at which Julia will run does depend on Julia being able to work out what type things are. But actually, Julia usually does that automatically. So if we think about this coin function, I never mentioned types there, but when I passed in a floating point number here, Julia knew that, oh yeah, you passed in a floating point number. Now here are, oh, I know that that's also a floating point number because it's the result of this rand function. And then, oh, I'm comparing 2 floating point numbers, so I know that that has to return a Boolean value. So let's just see. So there's actually a way you can see what Julia is doing. There are various ways that you can see what Julia is doing internally. So one of them is this macro called @code_warn type. And I'm going to run it with coin, say, 0.3. So what a macro does is takes a piece of Julia code and turns it into some other piece of Julia code. In this case, what it's doing is using some functions to look at what the Julia compiler thinks about this function. And so what you can see is that it realized that P, I passed in a floating point value, and then when I called rand, it returned this floating point value. And so it knows that comparing 2 floating point values has to give me a Boolean. And so the body of this function, it knows that it returns a Boolean. So Julia is actually doing what's called type inference to work this out, basically propagating the types through the function to work out what type everything is. And if it is able to do that correctly, then it will be fast. If it's not able to do it correctly, then it'll be slow.
Awesome. And then
good question. So the point is that actually what we want to do, what we aim to do, is write code where we don't talk about types as much as possible. In particular, you don't want adding like doing this, for example, adding a type. This is called a type annotation with this : : That's not going to change the speed at all. That's just pointless, basically. So people think, coming from other languages, that you need to make these type annotations on all the input parameters. That's not right. You should actually prefer not to do that, because then you can pass in other kinds of arguments as well. So what this is actually doing is just saying this function can only work if I pass in a float 64. but I just saw that it would also work if I passed in a rational number, which is not of type float64. And so I should not actually put this annotation on it if I can avoid it. Yeah, thanks. Was there another question?
Yep. So is push usually faster than concatenation, or they usually have similar performance?
That's a good question. So yeah, so if you come from some other languages, you might be used to doing things like, if V is some array, which I can write like this, you might be used to doing something like V equals V semicolon 4. That's supposed to take the array V and concatenate it with 4 and put it in a new array, right? So you can do that in Julia, and the answer is that's much, much slower than using push. So you should prefer push instead of this. Why is it slower? Because what it's doing is it's making a new array somewhere else in memory. It's copying over all of that information into the new array. All the information that these three numbers, it's copying those over into some new place in memory. Whereas what push does is it's actually more clever. It says, do I have any space left in the current place in memory where my array is? If I do, then I'll just extend the array, I'll just use that extra space that's available to me, and I won't need to copy the data. If there's no more space available, then only then will I need to copy the data somewhere else, and that'll be done automatically for me. But the way it does it is it reserves sort of extra space every time it allocates new memory. It reserves extra space, like something like twice as much space as it actually needs. And so you can do a lot of pushes before it needs to do that again. And so basically, if you what's called amortize the time you require, so you sort of average out the time you require to run these operations, it'll be almost as if you didn't have to do these reallocations. So it's actually very efficient. So push is implemented in a very efficient way. If you care about the absolute maximum efficiency, what you should do is pre-allocate your vectors. So you can actually say, this is like a technical detail, size hint v100, that will actually reserve 100 spaces for objects inside V, so that you can guarantee that, I think you can guarantee that it's not reallocating up to size 100.
Great. A question about the exercise they're working on. The
Yep.
instruction says run coin n equals 100 times. What value for p should they pass?
Oh, good question. I mean, choose a value, 0.25.
0.25 it is. Okay, and then why did you prefer int64 to bool?
Yeah. No, I mean, it can be bool, that's fine. Yeah. So what type is this value true? It's of this type bool with a capital B. That means Boolean. Just means a variable that can only be true or false. So yeah, I could have done bool empty vector. That's totally fine as well. Yeah.
Great.
I probably should have done that actually. Yeah. So you see that in this particular case, this is a bit annoying because I have to actually specify myself the type. And I just told you that Julia is supposed to do that for me. So we'll see in a minute a way to avoid specifying the type. So the best way to avoid it is actually this. So if you already know one of the values that you want inside your array, and you know that all of the other values that are going in the array will be of the same type, then you can just start off your array with a single type, a single object, a single value already in there, and it will generate an array of the right type without you specifying the type by hand. But of course, that's not our situation in this particular case. So that's why we started with an empty array.
Awesome.
Okay.
Does V need to be Boolean?
What do you mean?
I'm not sure that's the entire question.
Okay, I mean,
So we can move on.
so the point is that coin, just the way coin works, it returns a Boolean value, right? So you can return other value. So for example, if I wanted to make that into an integer, I could. So I can do int64 and I can treat int64, which is the name of the type integer with 64 bits. I can treat that as a function, and then it will actually do the conversion from this value, which is a Boolean. So let's actually do that more explicitly. R equals coin of, I don't know, B equals coin of 1/3, and then int64 of B. And that will actually convert my value true into an integer. So true is 1, that gives me 1, and false gives me 0. I can also convert it into a float 64, and it'll give me, you know, the floating point version of that. So floating point numbers are distinguished from integers by always printing out point something. Yeah, good question. So I can't actually see this Q&A tab for some reason. So please do. I can't see the questions for some reason.
Okay. There are quite a few.
Oh, I see. It appears somewhere else. Okay.
There. Okay.
Yeah. Go ahead.
So there are quite a few questions kind of about pre-allocation versus push or append. Yeah. Do you just want to talk a little bit more about kind of pre-allocation versus pushing?
Right. Yeah, sure. So, okay. So, yeah. So, okay. So I'm going to actually do the exercise. I think that's the best solution to talk about that. So, so run coin 100 times. So one thing I could do is v equals an empty Boolean array. And then for I in 1 to 1 colon 100. So this is a range in Julia. It means, you know, step from 1 to 100 with spaces of size 1, basically. So if you want to, so if you just ask Julia, what is 1 to 100, it'll tell you that it won't give you much useful information about it. If you type of that, it's something called a unit range. And it's a unit range, and this curly brackets mean that the type of thing that's stored inside this object is are of type int64, so integers. And if you want to turn that into, you want to actually see the values that are inside. Okay, so the point of this is that it's an object which is like a lazy, sort of a lazy generator object, which will, it doesn't store all the values from 1 to 100, right? So if this were 1 to 10 million, right? 1 to 10 to the 7, so I can use this single hat for power in Julia, unlike some other languages. I'm not going to mention any explicit, you know, I'm never going to talk about what happens in another language. I'll just say in some other languages, because people come from different languages. So, so this means all of the numbers from 1 to 10 to the 7. Okay, so I don't want to store all of those numbers in memory, because that's a lot of memory that I'm wasting, and all I need is something that counts from 1 to 10 to the 7. So this is one of those kind of objects where, but if I actually do want to see all of the values that I'm producing, I can do that with the function called collect. So collect will actually make an array in memory which contains all of these values, right? So now there's some space reserved in memory, some little box, you know, I can make like a box. Somewhere in memory, it looks like this. There's a box. So sorry, I couldn't manage to connect my tablet, so I'm not going to be able to draw very carefully, but very well. There's a box with some spaces, and now, you know, there's all of these values actually stored in memory. Right? Before, I didn't store those. I just stored the starting value, the stop value, and how much I step each time. Okay. But now with this collect, it actually made a whole array with those values in. Okay. So, okay, so yeah, so I was in the middle of explaining this for loop. So a for loop looks like this. For I, that's the name of a new variable that I'm introducing in 1 to 10. So instead of in, you can also use equals. For I equals 1 to 10, you can also use the mathematical symbol \in, and then press tab. So type \in, and then press tab. Press the tab key, and that will actually, as you saw, it will replace. Sorry. If I type \in and then press tab, it will actually replace this sequence of letters with this symbol. Okay, so if you like mathematical notation, you can use that. So I tend not to use that in for loops. I just write in, but I do use it to mean set membership in mathematical code. Okay, so now what am I going to do each time? I'm going to flip my coin with some probability. So I need to decide what probability I have each time. So let's put 0.25. But actually, well, the 0.25, I might need it some later time. So instead of putting 0.25, I should just make it into a variable and give the variable a name somewhere else. Okay, so I'm going to, so note that this variable lives sort of in the outside space, outside any functions. That's called the global scope. So this is a global variable, and then I'm passing that p into coin, and then inside coin there's a local variable that only lives inside the coin function that does this, that takes that same value. Okay, so I'm going to flip my coin, and I'm going to store that in my vector. So I can do that with push v and the value that I just calculated, c. Right, so if I do that, then I executed the code. So how do I know that I executed the code? Because this in gives me a number. Once it gives me a number, right? So when I'm just editing the cell, it gives me an empty box here. And then when I execute it, it gives me a number which tells me in which order these cells were executed. But you see that it didn't output anything, right? So for loops, so everything in Julia returns a value. Right? Every time I execute a statement, I get a value returned. But the return value of a for loop is nothing, right? So, so let's call it value equals 4. I can write that, and then the question is, what is the value of value? And it doesn't print anything out. But if I do print a value, then it'll tell you that the okay, value is probably a bad choice of word. Let's call it a val. So the value of the variable called a val is this special object called nothing, right? And that is of type nothing with a capital N. So other languages have similar things. So basically, yeah, as I was saying, so everything in Julia does have a value, it does return a value, does evaluate to a value, even a for loop, but the for loop has the value nothing, and it won't print that out. It won't return, you won't see that usually, unless you sort of make an effort to see it with this print. Okay, so let's look at the data. So we're supposed to have produced some data. So if we just type v, yeah, again, no print, right? I'm just going to type v, and it will output the value of v. So it's a bit annoying because it's this sort of long column of numbers. So I'll do v primed, and this prime just means transpose. So transpose just takes a vector that's sort of vertical and makes it into a vector that's horizontal. Okay, so it's this strange type that we won't worry about, but yeah, it's just a trick. So let's actually do exactly what I said not to do and do print, and then we actually see it without all the messy noise. So here are all the values of the coin flips, right? So 0 and 1. Okay, but when it's printing them out in this way, it actually uses zeros and ones instead of trues and falses. Okay, but okay, never mind. So we have actually managed to produce this data. Great. And then what I should do is actually put all of this inside a function. But before I do that, let's see some other ways of doing this operation. So this is such a common thing to do, right? You start, you have some loop, and at each point in a loop, you do something. It's such a common thing to do that there's a very nice short syntax to do that, which is we're going to make an array. So we need square brackets, and then we'll do coin of p, and then we'll put the for loop sort of inside for I in 1 to 100, and that's all. And so I'll do the same again. V equals this, v primed, print v primed. Okay, so this is a short syntax that's exactly equivalent to what I did up here. This whole for loop, reduce it. So the creating an empty array and then doing all of this is equivalent. Well, it's equivalent. It's not equivalent in exactly what Julia does. It's equivalent in the output it gives. So this is actually more efficient. Okay, so this comes back to the pre-allocation thing, right? So what I could have done instead of using this push, what I could have done instead was, for example, v equals zeros of int 100. So this will make a vector in memory of size 100 and fill it with zeros. Right? So there are my 100 zeros. So if you don't want to fill it with zeros, you can also do this this syntax. So if I can remember how it goes, undef 100, is that right? No. Yeah, so you can actually make a vector with undefined entries. So basically, whatever the garbage that is already in memory, that didn't work. Sorry, hint. No, I'm not. I don't remember exactly how to do it, but there is a way of making a vector with where. So the point is that filling memory with zeros is actually a bit expensive. So you want to just reserve the memory without filling it. So yeah, so that's the way that you can actually pre-allocate memory. And then how could I go along filling it in instead of this using push? So I can no longer use push because push will actually add an extra element into the array. So instead of using push now, I'm going to access an element of the array. So the ith element of the array, I'm going to set equal to C. So don't use push bang if already allocated. Okay, does that cover the questions, Mary?
I think so. Now we're getting some questions about the success rate function. Might be.
Okay, yeah, so let's carry on with the exercise. So we actually want to do all of that stuff in a function, right? So I said, make a function called coins with an S on the end, right? I'm going to run flip n coins with probability p. So I'm going to define that just using coin of p for I in 1 to n. Right? So this defines that coins function. So you can, of course, do it by using these for loops. But as I said, there's this nice simple syntax. So let's forget about using for loops if we can use this simple syntax instead. And then because it's so simple, I can just put it in a single line and use this nice single line function definition format. Of course, if you don't like that, if you think it's difficult to read, that's, so basically, people like writing short functions like this, but some people go too far and write very complicated short functions that it's very difficult to read because they made them so short. So I write them only when they're really simple functions. But basically, the idea in Julia is always make the functions as simple as possible. So I'll comment on that a bit later as well. Okay, so let's see how, run coins with these parameters. But again, I really want to take out the parameters and make them into variables, right? It just makes it so much easier to read the code. It's basically, you make the code self-commenting, right? So people often say you should add comments to code. I totally agree, but you should add comments when they're needed. Here, it's totally clear, I think, what I'm doing, right? Or I could write here number of coins, right? And probability, etc. Or I could, I could actually write here num underscore coins and probability. And then if I use proper variable names like that, I no longer need any comments at all because the code is self-documenting. Okay. Great. So now, what are we supposed to do? We're supposed to make a function success rate that calculates the proportion of times that the recovery was successful. Okay, so so what I'm thinking of here is you can think of these coins as, did the person recover? Did the person recover? Or you can think of 100 people, and at one particular step, I'm asking, did person 1 recover? Did person 2 recover? Did person 5 recover? And so the success rate is just going to be, the total number of coins that were true divided by the total number that I flipped. Okay, so how do I do that? So I need to find how many coins came up as true. So let's call this, flips equals this. So there's now a, so if I put semicolon, by the way, at the end of a line, it suppresses the output. I no longer see the output. But that's the only time you ever want to use semicolon almost in Julia. You do not put semicolon at the end of every line. It's a total waste of time. You can, but you shouldn't. I mean, it doesn't do anything. It doesn't harm anything, but it's just pointless. And it just makes it harder to read. Okay, but the semicolon here is suppressing the output. Okay, so now I want to count how many coins came out as true. How could I do that? So can we have answers in the chat or in the Q&A. Okay, yeah, so there's interesting. Yeah, okay, sum over the vector, yeah. Okay, so yeah, there is so of course I could write a for loop to do this for me, right? I could write a for loop, and instead of, okay, so I could even write a for loop and never store the values at all, of course. But if I've already stored them, because I'm going to use them for something else, then there is a function called sum. So if I just write sum of flips, it will actually count, it will do the sum of my vector for me. Of course, if I forget that this function exists, then it's perfectly easy to write a function to do that myself. I just go through the vector and add, all of the results up. So let's just do that quickly. So for I in 1, 2, now I have a vector. I don't want to repeat this 100, right? So, but I already have a variable which tells me how many coins there are. So I could use that, but maybe a better solution is to actually write length of flips, right? So length is a function which, I teach in Spanish in a Spanish-speaking country, Mexico. So I'm very aware that many people find the word length very difficult to write, right? So the Julia lets you not write this function, right? So just write this name. So just write len and then press the tab key, and it will automatically complete this name for you. So Spanish speakers often write len ht. I've never quite understood why, but that's what happens a lot. So, and English speakers, I think, as well, often write it incorrectly. So length, you just write len, which is easy to remember, and then tab, right? So length is a function, and it takes a vector, and it returns the length of that vector. Right? So, okay. So then I'm just gonna, so that's one way of writing it. So, and then, so what we need is we're actually gonna sum up all of these values. So I need some variable, some new variable to store the result. So I'm gonna say total equals 0. That's a new variable. And then every time I'm going to say, every time, what am I gonna do? I'm gonna add total equals total plus, and then I'm gonna extract the ith entry of flips. Right? And then if I do that, total will have this value 30. Now, if you try and do this in the Julia REPL, not in the notebook, I think depending on which which version of Julia you have, maybe you might need the word global in here, because this is to tell it that this is a global variable that you want to modify.
Awesome.
Okay. And then
David, one question. Yeah. It looks like at least one person using an older version of Julia is seeing true false instead of 0 1.
Okay, sure. Yeah. So I think that exactly the version of Julia might affect how these things are printed out. Yeah.
But no worries about actual
functions. There's no worry. Yeah, it's the same. It's just how it's printed. If you actually want to see the real value, when I print out flips as a whole vector, it does that. But when I print out the third, this means the third component or the third flip in the list in the vector flips, then it does print out false. So you can check, oh yeah, it really is trues and falses, not zeros and ones. So it's just zeros and ones because it's easier to visualize like that, right? It's easier to see the zeros and ones visually than seeing the trues and falses. It takes up too much space with trues and falses.
Awesome. And then one question, which kind of back to a little bit, but how to remove pre-allocated vector from memory. So we're creating all these vectors. Is there a way to clear out that memory?
Yeah, so that's a good question. So yeah, so if there's some vector like that, how do I get, and I've reserved a lot of memory for it, like 1 million, 10 million, 1 billion places in memory, how do I get rid of that? You can just do something like v equals 0, and then Julia has a garbage collector, which will realize that nobody is referring to this array anymore. And so it will mark that space as being available for reuse. And so there's no actual way of deleting it. You just sort of stop using it and make sure nobody's referring to it anymore, and then Julia will take care of it. Okay. Yeah, so you don't need to, do all this stuff about deleting objects after they're used, like in some other languages. which is very difficult, very annoying to keep track of. So Julia does all of that for you. That's the advantage of using a language which has this garbage collector. There are some disadvantages as well if you're doing some kind of real-time hardware stuff, but okay. What was I going to say? Yeah, so that's the way that we could write a sum function ourselves. That's one way. You can also not, here I had to do this one to length flips. That's kind of annoying. So you can also get around that by doing for I in each index of flips. So each index is an iterator that iterates through the indices in flips, right? So if I just do each index of flips on its own, right? So you should always keep asking Julia stuff, right? Julia can tell you a lot about what it's thinking. So I can just ask you, what do you mean by each index of flips? And it tells me, oh, it's this thing, 1 to 100. Okay, so even if you don't know exactly what's going on there, oh, it's like something that counts from 1 to 100, right? And this lives in base. So base is the sort of like the main basic pieces, basic functions in Julia that give it its functionality. And this dot means it's inside this module. So base is a module in Julia, and there's this 1 to object that lives inside Julia. So you might, if you're lucky, so I haven't mentioned this yet, you might be able to ask for help on that function, and indeed you can, and you hopefully the help will help you. If it doesn't help you, you might want to suggest a way to modify the documentation in such a way that is easier to understand. You can do that by making a pull request on GitHub, or raising an issue, or go on one of the Julia fora. The Julia community is very helpful. So if you go on the discourse page, site, forum, or you go on the Slack, or for JuliaCon, there's going to be a Discord forum. You can say, oh, I think this documentation is not very helpful, and then people will help you improve it. Okay. So I think, yeah, I think we might want to take a break now. So let's take a 5-minute break. Or yeah, I think that's a good idea to take some breaks. Let's take a 5-minute break.
All right, so we'll start again at 10 past the hour.
Exactly. 10 past whatever time it is now. Well, in 5 minutes, yes.
Yeah.
Yeah, because there are some people who it's not even on the hour, actually, right? In India, I think that, for example, in some parts of India, they have a half-hour difference of time, like 9.5 hours difference.
On one time zone, but I think it might be a half hour off.
Right. So yeah. So anyway, in 5 minutes, we'll carry on. So yeah, if you have more questions, just keep posting them, and we'll answer them when we get back. Okay. Thanks. Okay. Can you see my screen and everything's still fine? You can hear me?
Me.
Yeah? Okay. Just let me know if there's any problem. Okay, so yeah, just to confirm, this is being live streamed to YouTube and right? That's correct, right?
Yep.
And yeah. Okay, I see. Yeah. You can see the notebook, right?
Yes.
Okay, thanks. Yeah, so this is being live streamed to YouTube, and you can just catch up later if you need to leave or anything. Or as I said, you can even rewind the YouTube presentation. Although, of course, then you're going to miss whatever's going on. Okay. So there was a question on the Q&A about broadcasting. So broadcasting is something very neat in Julia. So let's just, I wasn't actually going to talk about it, but let's just mention it briefly. So what is broadcasting? So I have these coin, these coins that I'm flipping, something like that. It gives me a vector. And now what I'm trying to, well, okay, so no, before I even do that, sorry, I have these random numbers, some number of random numbers. So if I do rand of 100, it actually gives me 100 random numbers. Right? So let's say rand of 10 so we can see what's going on. Rand of 10 gives me 100 random numbers between 0 and 1. By the way, if I do rand of 1 to 5, 10, right, where 1 to 5 is one of these range objects that we saw earlier, that actually gives me 10 random numbers between 1 and 5, random integers. And so you see this is an example of how we can use rand, the function rand, in different ways by giving different combinations of arguments. These are called different methods of the rand function, different versions of the rand function. So that you can think of the rand function as a whole as being a patchwork of different versions of the functional methods that we can use for different things. But the point is that they're all somehow doing some kind of random generation, right? So rand is a function that's designed to do some kind of random, generate some kind of random object. And if I call it in different ways, I can generate different kinds of random objects. But so the idea of these generic functions, as they're called, these functions with many methods, the idea is that all of the methods somehow do the same kind of thing. If they don't do the same kind of thing, they should be a different function with a different name. And we'll actually be writing our own methods later. Okay, so yeah, so if I want to compare, one of the ways, what I need to do for my coin flips is compare all of these numbers to, say, the number 0.5. So if I try and do that, I could try and do that by writing rand of 10. Let me move down. Rand of 10 is less than 0.5. That would be, natural if you come from some other languages. But in Julia, that will give you an error. Why? Because rand of 10 is a vector, an array, and 0.5 is a number. And it does not make any sense to compare a vector to a number, mathematically speaking, right? It makes no sense to do this. What makes sense is to compare the elements of the vector to this number. And so that has a different syntax in Julia. I write something different. I write a dot here. Dot. So the dot means broadcast. Means run the thing, run the function, element by element. That's what broadcast means. So when I do that, it compares each of the elements, right? So I can think of this as point. And so this is a point-wise operation, right? So point dot means point. This is a point-wise, which means element-wise operation. Okay. So that's very useful syntax in Julia that you'll see all over the place. This is the way that you do vectorized operations in Julia. Right? So in some other languages, you need to do vectorized operations. In other words, you need to write operations on vectors instead of on numbers in order to make them efficient and fast. In Julia, that is not the case, emphatically not the case. You can write, the for loops that we wrote before, if you put them inside a function, are going to be as fast as these vectorized operations. So you do not need to write vectorized operations. And it's often very difficult to write certain operations as vectorized operations. So, but in Julia, so at some point in the evolution of Julia, people avoided vectorized operations, but now using this dot syntax, you can use that on any function, in fact. So for example, I can do rand dot of 1 to 10. What will that do? That's actually a bit confusing. Okay, let's not do that. Okay. Okay, so for example, f of x equals 2 times x. So I can actually write that as 2x. You don't have to put the multiplication sign in if it's a literal number. And then I have f dot of 1 to 10. What is that going to do? It's going to apply this function f element by element to this range. And it'll give me 2 times each number in that range. Right? So this is just a general function that I just wrote. And I can apply the dot operator element by element to that with that function. Okay, so that's called broadcasting. And I could have used that to do my coin flipping. Okay, so there are some other things down here. And in particular, yeah, there's some plotting and stuff. But I think we should move on. I think we should, well, no, it's kind of interesting. Yeah, so let's just do this quickly. So why don't you try these functions? Try writing these functions. So write a function recovery time. So yes, we want to ask the question, how long does it take for a single person to recover? So we're going to be flipping, we're going to start off with this person infected. And we're going to flip this coin every day and say, how many days does it take until that coin comes out as true? Right, so try and write that function. And then it says plot the probability distribution of recovery times. So run this function a lot of times and then plot a probability distribution. So I guess we were supposed to do that upstairs with the success function. Oh yeah, sorry, I haven't finished that yet. Okay, sorry. Let's go back and do the successes function. Yeah. So I got bogged down in. So success rate of NP, what is it going to be? I'm going to sum the vector that is produced by coins of NP. So I'm going to flip my N coins that I already defined. That gives me a vector. I'm going to sum up that vector with the sum function. And I'm going to divide it by N. So that's a very short way of writing this function. So let's see if it works. Success rate of 100 and 0.25. So in this particular case, 1/3 approximately of the 100 coins came out as true. But if I run that again and again, I'll get a different answer because it's a probabilistic or random or stochastic process. Okay, so what do I want to do? Well, I want to run this function many times again, right? So inside each of these functions, I'm flipping many coins, but now I want to run this function many times. And so how can I run that function many times? So we already know how to run functions many times, right? So I'm going to put n equals 100, p equals 0.25. I'm going to run this function success rate with n and p, say 1,000 times, right? So let's call number of times equals 1,000. What I'm going to do is an array comprehension, success rate np for I in 1 to num times. And I'm going to call the result something like data. Not a very good name, sorry. It's difficult to think of good names. I mean, data is rates, let's say. Rates equals this, right? And now what do I want to do? I want to, well, first of all, I want to look at the data by I. And what can I see when I look at it by I? Oh, well, there's some values 0.2, 0.3, 0.24, right? So these are the different success rates that I'm getting from each experiment. So basically, each of this success rate basically runs one whole experiment where I flip 100 coins. And then I'm getting out all of these different numbers because it's a random process. And so now, just by I can see, oh yeah, so it's something like, it seems to be giving me something between 0.2 and 0.3, say. But I can't really understand anything by visually inspecting the data. What I want to do is plot and visualize the data. So I'm going to use the plotting package called Plots. Right, so this is a package called Plots.jl. So if you need to install the package, you do it like this. This is to install the package. So this is a backwards square bracket and then add plots. Alternatively, you can do using package with a capital P, that's the package manager in Julia, and then add package.add and the string plots with capital P. this. So we need to sort of, so now we're going to look at plotting. So we need to install the plots package. This is only once. You only do that once in your life, right? Once in the current installation of Julia. Once for each Julia installation. Just once you install it, but then every time you need to load it in every Julia session. Right, so this downloads the code and puts it on your computer. This using package add plots, and then using plots actually loads the code and basically defines the functions that are defined inside the package. Okay, so what functions are defined inside that package? There's one called plot. So let's just plot the data. Right? So actually I'm going to use scatter because they're discrete data points. So let's just scatter the data that I just generated, which is called rates. So this is a function inside. So scatter is a function from the Plots.jl package. So it takes a few seconds. The first time that you run a plot, it has to compile some of the code in the package. So the reason that Julia can be fast is because it usually compiles functions to machine code, and that takes a while. So it's slightly annoying. People are working on improving the performance and improving how fast loading packages takes. There has been already a lot of improvement. Okay, so that's what the data looks like. So we can see that, yes, it's clustering around some middle value that's something like 0.25, but there's, sometimes there really were a very large proportion of successes, a large proportion of heads, and sometimes there are a large proportion of, a very small proportion of heads, right? So how can we look at this data in a better way or different way? We can use the function histogram from plots, from plots.jl. So we just type histogram of rates, and it gives me, it chooses some width of the bins for the histogram. I can also tell it how many bins I want. So there's 100 bins. So there you can see the discreteness of the data coming in. And so that is the probability distribution. Well, it's not quite a probability distribution yet. I have to normalize it. So make normed equals true. And then I get a probability distribution of this quantity. So it just tells me how often do I see the value 0.25? How often do I see, so it's like, so let's cut down the number of bins again. How often do I see a value between 0.2 and 0.25? The answer is, I see it. Okay, so sorry. So if I do normed equals false, then I saw it, 350 times out of my 1,000 times. And so the probability of being in that region is 1/3 or something. And we expect it to be about 1/4, so that's about right. And as you take more and more data, you'll get a better result, right? So then the idea was to use the interact package. So this is a very nice package for doing visualizations. Unfortunately, it's sometimes, some people have trouble with the package. It doesn't always work correctly. So what is this package? How do I use it? So this is what I showed in the visualization at the start, right? I showed a slider. This is what interact will give me. So if I do for I in 1 to 10, I squared end, then it should give me a slider. So it's taking in this is again a macro with this @ sign. @ sign always means macro. So it takes in this piece of Julia code and it transforms it into another piece of Julia code. And that piece of Julia code is designed to to visualize this slider and allow me to move it. And when it moves, the output also moves, also changes. So by the way, if I do @macro expand of this macro, I can actually see what is the code that Julia generated automatically. So it went in, it picked apart. So Julia is pretty, has some heritage from the Lisp language. Well, it is sort of a version of Lisp in some sense. And so basically it's able to treat its own code as something that it can manipulate itself. So it's taking in this piece of code as a Julia object, and then it's manipulating that object and producing this new piece of code. So you can see that what it's doing is inside it's doing the same calculation that I wrote, but here it's changed the for loop into some widget. So this slider is some kind of widget. and well, you can look at that code later if you want.
Yeah.
Okay.
David, people have had a bit of trouble getting Interact working. Is there a good debugging tutorial on that?
No,
or
it's frustrating. It's a bit flaky, and it's not very clear why, at least to me. So sorry if it's not working for you. There's not much more I can say. You can try. The only debugging tool that not even debugging, the only tool that I know is do cell all output clear, then save the notebook with Command S or Control S, then restart the kernel and run all, and maybe it'll work. I had to do that before. But if it's the first time you're using it, it shouldn't happen. So I really don't know about that. Sorry.
And then will you be sharing your kind of filled in version of this notebook after the workshop?
Yeah, just remind me to do that, please, at the end. Yeah, actually, right. So if you remind me when we finish this notebook, I can immediately upload this notebook. And well, I don't know if that's useful. Okay. And so,
and then explain the difference between functions and macros quickly.
Right. So a function, a macro takes a piece of code and turns it into a different piece of code. And then that new piece of code is run instead. So basically what this is doing is sort of replacing this piece of code by this other piece of code that was generated down here. A function is just a normal, much more normal thing. Macros are very special, very weird. You shouldn't worry about them for now, basically. Functions are just normal. They take in a piece of data, a number or a string or whatever, and they do something. They massage, they manipulate that piece of data, and they spit out some new data. Macros, because the difference is in macros, the data that they're manipulating is actually a piece of Julia code. That's the difference. It's like a super function. But anyway, let's not worry about macros. That's for a different tutorial. By the way, if you do care about macros, I do have a tutorial from last year at JuliaCon and from 2016. So some of the syntax has changed, but the basic ideas are valid. Okay, so we can use this at manipulation. So it's like the point is that normally when you write this for loop, it just does a for loop, right? It just iterates through these values and calculates I squared for each one. But this at manipulate is doing something special. It's taking that for loop and changing it into something very different, which is this slider. That's what a macro. That's the special power of a macro. Okay, so we can put. So what are we going to do? We're going to actually. We want to take a histogram. So this histogram that we just did, we're taking a histogram of all of the rates data. So what I want to do instead is take only some of the rates data. Right, so I'm going to take the rates data from 1 to number I, or let's call it n, to number n. Right, so sorry, don't want the macro expanded there. And so the point is I have a plot inside my manipulate now. And so this notation means take this part of the array. So just from 1 to n, and just use part of that data into histogram, right? So as I increase the value of n, you can see this data filling inside my histogram. That's the point. Right? So I think that's pretty cool. And it's so easy to do that and make this beautiful interactive visualization, as long as interact.jl works for you. So there is an alternative solution. And I thought about using this, but I decided not to because it's still pretty new, which is a package called Pluto.jl. This is a great package. It's pretty new, and it's completely unrelated to the Jupyter notebook. It's a Julia package, which provides you with an interactive notebook-like environment, but it's not the Jupyter notebook. And it has a lot of advantages if you're coding in Julia. And their interactivity is built in a very simple way, well, very neat way, and everything can be interactive in a much more serious way than in the Jupyter notebook actually. So I decided not to use it this time because it's still a bit new, but maybe I should have. Okay. There's alternative and really great solution, but it is pretty different. So, because people are used to the Jupyter Notebook, some people, I thought we would do the Jupyter Notebook. So, yeah, so, let's have some more bins. Let's have some more data. Oh, sorry. I don't understand why it does that. So where was my definition of rates? So let's just increase the number of times and increase the amount of data so that we can see a nice histogram. So let's say 10 to the 5. And now I'm getting a histogram with a lot more data. And you can see that indeed it converges to the histogram starts looking more and more like a bell shape, a normal distribution. Okay, great. So I think that's probably all we want to do on this notebook because we need to move on. Okay. We have 2 hours left and we have 4 notebooks left. Yeah. So I'm going to move to notebook number 2. So if you're inside the notebook, you can just do open, file open, and then choose this number 2 notebook. So we're going to look at generic programming with random walks. Okay. So we want to do this model of people moving around. And the easiest way to model motion is just randomly. So I'm going to have a person or a point, and it's going to jump in some random direction. So if it just lives in one dimension, it can jump right or it can jump left. And for simplicity, we're just going to assume that it lives on the integers, the whole numbers. And so what does my algorithm look like? So I'm start at some point. So I have to actually know how to initialize my walker. I'm going to say, start my walker at point 0. So it's going to have some kind of position variable, which is going to be equal to 0, say, or equal to 100 or wherever you want to start. And then at each step, I want to move the walker. So it's either going to jump right or jump left with equal probability. Then I want to store that position because I want to know where the walker went in its history. And so the algorithm is just going to be this simple: initialize it, then at each step, move it and store the new position, and then repeat. Now, where does my walker live? It might live in 1 dimension. It might live in 2 dimensions on a grid. It might live on some kind of network. Or, I might be doing some other strange thing like, I don't know, Google PageRank used to use, at least, I don't know if it still does, a walker that jumped around on the graph of all of the web pages connected together and jump around in some special way to explore that structure. So the point is, I'm going to have different types of walkers that live in different worlds. But if I start writing my algorithm, what I'm going to realize is that each of the algorithms for making all of these walkers jump looks the same. And so what I actually want to do is work out how to write the function only once, right? I'm going to write a function called walk, which simulates a walk, but I only want to write it once. So this idea is called generic programming. It's going to be independent of which kind of walker is moving around. Okay, so here's some example code for how to simulate a walk. So this first line is a doc string. It's a string that you put outside the function, unlike in some other languages, just before you define the function. And that will, so when I execute this code and then I say question mark walk, it will actually output the help for this. This is like help text for this function documentation. Okay, so what am I going to do? I'm going to initialize my walker by calling a function called initialize, and I'm going to assign that to a variable pos. Then I'm going to make an array that stores what the current value of pos is. So we saw that if I make an array with this square brackets, a vector, this will make a one-dimensional vector with exactly one thing inside, which is this current value of this position. Then I'm going to move my walker, right? So I'm going to need to tell it what is the current position, and I'm hoping that move will give me back the new position. And so here I just said new pos equals move of pos. And then I'm going to store it in trajectory with this mechanism that we have been talking about with push. So for example, here it's not clear how you would write this in a vectorized way. I mean, it would just be sort of you would have to have some weird special function that knew how to do this in a vectorized way. Because I'm moving at, oh no, sorry, in this case, it is clear how to do it in a vectorized way, but you have to think about it in a different way with cumulative sum. Okay. But later on, we'll have examples where it's really totally unclear how you would write it in a vectorized way. And the point is, in Julia, you don't have to. You just write the for loop and it'll still be really fast. As fast as anything else, at least as fast. And then there are talks about that, about how to make for loops even faster. There's going to be a talk on the loop vectorization package. Okay, so and then at the end of the for loop, we're going to update the current position just by making it equal to the new position. And then at the end, we're going to return this vector of trajectory that we calculated. Okay, so hopefully it's clear what that does. Okay, so I actually was able to define this function just now, right? So when I execute this, I define a function called walk. Okay, so let's try calling the function. So I'm going to say walk. I want to walk with 100 steps. And it immediately gives me an error. And it says initialize is not defined. Okay, so if I have a big piece of code, then I need to know where is the error occurring. So if I look down here, I see this stack trace. So that's telling you which functions were called and which line they were being called on, right? So where is the error? The error is here. In the function walk, I'm calling it with an integer, right? Here's the integer. Julia knows it's being called with an integer. And it's telling me it's in this input cell number 4. And this :3 means at line 3. So if I go up here, I see line 3. Oh yeah, there's initialize. I'm calling initialize, but I haven't defined a function called initialize yet, right? So I'm able to define this function without having defined the functions that I'm calling from inside this function, walk. But once I try and call the function, of course, then it will try and call these functions. And so it in that moment realizes that these functions are not yet defined. So now we need to define those functions. So let's think about a one-dimensional walker. We're going to define initialize, and we're going to define move. So here are some example definitions for a one-dimensional walker. So initialize, they're just these simple one-line functions. Initialize parentheses equals 0, right? If I just do initialize equals 0, that will create a variable called initialize. That's not what I want. I want a function called initialize. So I have to put the parentheses. And then I'm defining at equal to 0. That means when I call initialize like this, right? Remember, if I just put the name of initialize, it'll just tell me that initialize is a function. I need to put the parentheses to call it, and it'll return the value 0. This is the output of the function, is returning the value 0, right? So this equals 0 means, when I call it, just return 0. Okay. And then I'm going to do a random jump function. What does that do? It just generates a random number, which is either +1 or -1, right? So I can do that like this, rand of this thing. So this thing in parentheses is a tuple or tuple. So what is that? It's like an array, but it's a fixed size, and it has defined types for each entry of the tuple, and the types can be different in different places. So this is a very efficient data structure in Julia. So for example, I could put an array here, right? So if I put rand of -1 + 1, right, it will actually generate a random number chosen uniformly from all of these options inside this vector, right? Like if I have a 5 in here, when I keep running that function, it'll generate 1, -1, or 5 with equal probability, right? But it turns out that, okay, that's going to have to allocate an array at each step. And so instead of doing that, I should use a tuple instead, and then it won't have to allocate anything, and it'll be much faster. Okay. So by the way, I'm not going to talk about benchmarking, but to benchmark, in other words, to see how fast a function runs, you should use the benchmark tools package. I don't think I'm going to really go into how to do that. Okay, so I just made this random jump function, okay? But now we want this move function. And what is the move function supposed to do? It's supposed to take in the current position and return the new position. And so what is that going to do? It's just going to take the current position and add to it the result of the random jump function, right? So of course, I could have written this, right? I didn't have to write this intermediate random jump function. I could have written it like this, just straight away. And you might think it would be more efficient to do that because I can avoid the overhead of calling a function, right? So in many languages, calling a function actually costs you sort of time and memory. You want to avoid that if you want good performance. But in Julia, it's completely fine. And in fact, it's a better idea to write these tiny functions. And what will happen is that Julia will automatically inline these functions, which means that it will literally do what I just did for you. So it will literally copy this code and replace this function call with that actual code that's being run. That's called inlining. And so Julia will do that for small functions. And so you should not fear writing small functions. On the contrary, you should write functions that are as tiny as you can get away with. So here are like the world's tiniest functions, but you see that, just by combining these two functions, I get some good functionality, and it's still going to be efficient. So this is one of the major pluses of Julia. And it's just makes everything super clear, right? And so the reason I introduced this random jump function was actually because later on, we're going to use it again, right? And so we don't want to copy and paste code. We want to reuse a function instead, right? So now we can move our walker, right? So if I start at 0, then it can move somewhere else. And now I have to take that somewhere else and move again, and then move somewhere else. Okay, and that's the idea. So we're going to repeat this a lot of times. Okay, and so the point is now that I've defined those functions, I can actually use them by calling this walk function. So walk of 100 will give me this long vector. And again, I'm going to use the prime to get the to print it out in a more useful way. Okay, and we see that, okay, yeah, it's moving around and doing whatever it's doing. So let's actually plot that. I'm just going to, so there's this plot function. It can either take one argument or two arguments. If it takes one argument, like here, or like the scatter that I did before, it will take the x-axis as being just the index into that vector. So the numbers 1, 2, 3, 4, etc., however long the vector is. And the y-axis, the ordinate will be the height. The height will be the value of this vector at that point, right? So again, because this is a new notebook, it's a different notebook, so it has to recompile plots again. Okay, so yeah. Okay, so there we see a nice picture of a random walk. And then if I use plot bang, then that'll add another one on top. And by the way, if I want to do that several times, so I want to plot several trajectories, of course, I would try and use a for loop. So let's plot 10 trajectories. So what I would do is make an empty plot, first of all, and we're going to turn off the legend or the key, right? This box here, because it's just going to be annoying. So that's with leg equals false. That's a keyword argument. So I specify the name here, legend equals false. And then I'm going to do for I in 1 to 10, plot this walk. Plot bang adds to the existing plot. So this bang means modify the existing plot. Okay, and then end. Okay, and we're expecting to see some beautiful trajectories, and what we see is absolutely nothing. Oh dear. Why do we see absolutely nothing? So, usually I would be asking more and more questions and having much more interaction with the audience. Of course, in this particular, setting, that's very difficult to do. So sorry about that. So the answer is because what is happening is that Julia, this for loop, is returning nothing. And so it's displaying nothing. And what I wanted to display is the plot. And so one of the ways of doing that is to just call the plot something, P, and at the end, I'll just say evaluate the object P. And the object P accumulated all these plots, and so then I see this beautiful plot coming out. So this is a very important thing to remember when you're doing multiple plots like this in a for loop. You just have to, finish off by re-evaluating the plot object. So another way of doing that is just to write plot bang with nothing, and that will have the same effect. So that just like adds nothing onto your current plot, and that is enough to evaluate the current plot object. So there are various plotting packages in Julia that are great. I just have got used to using Plots.jl, and it has some advantages and some disadvantages as usual. And this is using the GR backend, which is pretty fast. But there are some other so one of the nice things about Plots.jl is that you can switch to using another plotting package. For example, you could try and use Plotly.js. It probably won't work because I don't have it installed, but Plotly.js is an interactive backend where you can actually zoom in. So that's pretty nice.
David, we just got a question on is he also considered a data frame? Maybe nice to have a quick detour into kind of data frames in the Julia ecosystem.
Have I considered a data frame? Did you say? Yeah. For what? For storing the data?
Yes.
Okay, so yeah, good question. Yeah, I don't tend to use data frames myself. Many people do. I mean, I use data frames, for example, if I'm loading some data, for example, some COVID-19 data, then I would definitely load that into a data frame. If you're interested in that, then the first lecture of this course that I referred to, the MIT course, which I linked to on the homepage of this, the repo of this workshop, the first lecture, we actually load the data and use data frames to process it. So I would go and watch that if you're interested in data frames. I'm not going to talk about them in this workshop. There are plenty of other workshops on data frames as well.
Great. And I just want to throw out that dataframes.jl is a Julia package. It's not a standard library. And there's a lot of great documentation on it in other places.
Yeah, so it's equivalent to sort of using data frames or data tables in other languages. Has very similar functionality with a sort of more Julian feel, a more Julia-ish feel. Yeah, thanks. Good question. Okay, yeah, so usually, you would use data, I would use data frames if I had data that was like, had different types floating around. And, I have a country that has a country name, and I have some dates, and I have data, and I have population, I have all kinds of different information, and then I have several countries with those things. Then a data frame is the right tool to use, yeah. Okay. So we've got this nice simulation, and it works great as long as I'm in one dimension. Now, what about if I want 2 dimensions, right? So I want to do exactly the same thing, but I want my walker to be able to move in 2 dimensions. So if we look at the code for walk, of course, I wrote it in such a way that I never talked about the fact that we were in 1 dimension, right? All I did was call a function called initialize and store that somewhere, and then call a function called move and store that somewhere. And so if I just change those functions, initialize and move, I can use the same exact code for 2 dimensions, or for a walker moving on a network, or for any other kind of situation. Right, so let's do that. So what we would like to do is, okay, so here's a function called initialize 2D. So I'm going to use standard Julia vectors. That's not the most efficient thing to do. You should really use the static arrays package, but I'm not going to talk about that, because we have short fixed length vectors, right? If we're talking about a point moving in some number of dimensions, you should definitely use static arrays.jl. It'll be much faster. So basically what that is inside, it has a tuple inside of an actual Julia vector. So the difference is that a standard Julia vector like this can be extended, can be, its size can change, as we saw. You can add things to it, you can remove things from it. And so it turns out that means that it's much slower to actually manipulate these objects in the way that we need. Okay. But so we have these 2-dimensional versions, right? So I'm starting off at the vector 0, 0, the origin in 2 dimensions, and then I have moved 2D. It takes in the current position, which should be a vector, and then it extracts the first component of that vector and adds a random jump to it, and extracts the second component and adds a random jump to that. Okay. So let's evaluate those functions. So, okay, so let's just check that they work. So I'm going to say initialize 2D. And it will return this vector 0, 0. And I'm going to say move 2D from the vector 0, 0, and it'll jump from that position to some other random position, random neighboring position. Great. So now, how can I use those in my walk function? So the problem is that inside the walk function, I called a function which was called initialize without the 2D. And I called a function called move without the 2D. So I want to somehow, force my walk function to use these functions. So one way I could do that is by rewriting my walk function and copying and pasting it and changing the name initialize to initialize 2D and changing move to move 2D. And that would be a terrible idea. I mean, it's a good idea, maybe once. Maybe once you should do this and copy and paste the code. And then suppose that somebody comes and tells you, oh, there was an error in your initial function. Well, now you have to fix the error not only in your original function, but also in the new function. So you're going to just be wasting your life, changing things in too many different places. So what should we actually do? Well, we should tell the function, you should please use the function initialize 2D when I asked you to use the function initialize. So the way we do that is like this. We're actually going to make initialize and move that used to be sort of names that I was calling from outside the function. We're now going to make them into local variables that exist only inside the function, right? So I'm just passing in the names of the functions that I want to use as parameters to my walk function. And then I'm, treating those names, initialize and move, as if they were functions, right? So this is actually going to define a new version of the walk function, a new method of the walk function. I can see that with methods of walk. I've got my original version that just has one argument, and my new version my new method that has 3 arguments that I just defined. Excuse me. So I'm using this deep copy because now I have vectors lying around and I want to be able to copy the vectors. Okay, and so this is like this is a pretty moment. I mean, like brain expanding moment. So we're passing in a function to the walk function, right? So how would I actually call that? I would call that like this. Walk initialize 2D, this 2-dimensional version that I had, and move 2D, and this is the link to the walk I want. And let's see if it works, and it does. Right, so what is it giving me? It's starting off at the origin, 0, 0, and then it jumps to 1, 1, and then it jumps again, etc., and it jumps 10 times. And it gives me an array of arrays. In other words, a vector of vectors. Right, so if I call, traj, like trajectory, equals this, then let's just look at trajectory number 1. So the first element of trajectory, the first component is itself a vector. So I have a vector with vectors inside. But what I really want to emphasize is that what happened is really we called this walk function and we passed in this function name or function object as an argument. And so what happened was inside the function, this name initialize now refers to this particular 2-dimensional version of the function. Okay, so here's an exercise for you to do. So suppose that there are 2 walkers in one dimension, one of which starts at position 0 and the other starts at position 2. Write a function encounter that runs until these 2 walkers meet each other. And then there's some data analysis you can do that we'll just leave for homework. So I see that there are some more questions. Let me just have a look, see if I can see them. I can't.
David, one of the questions is, could we have defined move with the same name and different arguments, a vector in one case and a single element in another, and would it still work?
Yeah, so good question. So so many questions. I don't see it. Okay, so yeah, so if we had, thanks, good question. So if we had defined, what we could have done here is instead of initialize 2D, I could have just called this initialize, right? And I called this one move. But because they're taking the same arguments, the same numbers of arguments, I would actually overwrite or replace the original versions of the functions. So I would now be able to do a walk in 2 dimensions And that would work fine with the original version of walk, but I could no longer use the functions in one dimension because they've disappeared, because I overwrote them. Does that answer the question?
I think so. I'm wondering if it's also thinking about kind of type-based dispatch.
Yeah. So that's what we'll do in the next work.
Sorry, I'm skipping ahead.
The next notebook. Yeah, exactly. So this is showing you, this is a very useful technique to pass functions into other functions. Sometimes useful, but this is definitely not what I'm suggesting that you use all the time. That's what we'll see in the next notebook. This is sort of just to get us thinking about how to do generic programming. Okay, so let's, so I hope you had a chance to do this. I have to press on because time is ticking by. So there are two walkers in one dimension. So, so what are we gonna do? We're gonna write a function encounter. So this is not really going to use actually our walk function particularly. Well, you could use it actually. Yes, you could use it. That's kind of neat. So, so you could just do a walk of my this two-dimensional walk is actually, if you think about it, each of the components. So the 0. So if I look at the first component of each answer, 0, -1, -2, -3, it's actually a random walk in one dimension, and the other one is also a random walk in one dimension. So actually, all I need to do is start them off at the right position. So that's one way I could do it, or I could just go ahead and make two separate walkers. So let's call them W1 equals initialize, and W2 equals initialize. Except I'm saying that W2, walker 2, should start at some other position, right? 2 instead. So actually I want to do initialize and pass in 2. And I realized, oh, I hadn't defined that yet. So what can I do? I'll just define it. Initialize, at position 2, at position X is just return the value of X, right? And so now, I mean, it's a bit silly to write it like this if you like, but it's going to reflect what we're about to do in a minute. And I'm doing this in totally the wrong place. It should be down here, sorry. Okay, so now what do I want to do? I want to move those, right? So at each step, what am I going to do? So I won't go through and write the whole code. You can do that for homework. At each step, I'll just do W1 equals move of wherever W1 is, and W2 is move of wherever W2 is. And now I want to compare their positions to see if they have met. They haven't met yet, right? And that's how I would do it. And I would write a function and then return the time it took until they met. And then I would look at the probability distribution, and you should find something very interesting, actually. So that's a whole nother, but yeah, that's not so much about Julia, so we'll leave that for another occasion. Okay, great. So now this looks like a nice solution until you think about this problem. So suppose we have a walker, W, and it starts at the point 3, and then we would know how we want to know how many times does W pass through the origin, up to some final time. Okay, that's the question we want to know. And so what we need is a counter, right? We need to count every time. We need to check after every move. We need to do something additional, not just move it, but also check. Has it reached the origin? Has it reached the origin? Has it reached the origin each time? And if it has, we want to accumulate that information in a counter. So we need to store that information somewhere. And the question is, where can we store it? And the answer is that in my current way of looking at things with these functions that I'm passing into this walk function, there's no really real way of storing this information. So that's not true. One solution would be to use a global variable. That would be, the easy way to solve the problem. But global variables are bad because they make code that is hard to read and hard to understand because you're manipulating something that sort of belongs to somebody else. Each function is going to be manipulating the same data, but it sort of belongs somewhere else. And so what's happening in the code, you can't understand by just looking at a particular place. in the code, right? You have to sort of understand the whole structure of the whole code all at once. So, okay, so there's another solution, which is a let block. You can go and read about that. I don't want to go into that now. Anyway, the point is that we're left feeling like this is not the right solution, right? Passing in these functions is not going to cut it. So let's move to the next notebook to see what the correct solution is, like the good solution. And the good solution is composite types. So this is where we're going to really get into Julia's types and see why we should use them to make our code better, right? So if you're coming from an object-oriented programming language, then you're probably used to using types, and a lot of things will be similar, but some things will be very different and very important to understand how they work in Julia. So what is a composite type? So I'm going to just do a little annotation. So the idea is we want to have some way of talking about a walker, and that walker might have some extra information, like the number of times it visited 0. Or actually later on, it'll have this information about, is it infected or not, right? So basically what we want is some kind of thing, right? And inside the thing, we want some information. So we want the information about its position, and we want the information about the other information, like, for example, is it infected? So sorry, I can't draw very well with this. Right, so I'm going to have these sort of two pieces of information inside this object, and I want to think of this object as a walker, right? This box or this bag that I just drew is a walker. So I can actually type that, I guess, instead. Yeah. Okay, better. So inside this bag, I'm going to have a position. Is going to be a variable stored inside the bag. And I'm going to have a infection status. Is it infected? And those are both going to live inside the bag. And that bag is going to be what I'm going to call a walker. So this is a walker. That is an object of type walker. That bag, right? That is what an object of type walker is going to look like. So that's the idea. So we're going to aggregate or collect all the information about my walker into one sort of thing, one bag, one box, one container, if you like. Okay. So let's see how to do that. So it's going to give us, so we're going to define a template for what does a walker actually look like. It looks like this. It has a position and it has whether it's infected, for example. Okay, so the way to do that in Julia, so I'm going to have to clear this so I can move on. The way we do this in Julia is with this syntax. So we're going to define what's called a struct. So the word is short for structure. And I'm going to give it a name, which is walker2d. And we always use initial capital letters or capital letters at the start of each word in the name of a type. And we do not use capital letters in the names of variables in Julia by convention. And so inside, I just tell it what is going to live inside. So in this case, I'm thinking about a walker moving in 2 dimensions. It's going to have an x coordinate and a y coordinate that are both integers. Okay, so when I define that, then Julia doesn't tell me anything. It doesn't return anything. But then I can just ask, well, what is this walker2d thing? If I just evaluate this walker2d, it tells me, oh, it's walker2d. Okay, so what is that? It's the name of a type that I've just defined. So this is in Julia, there are types that we've already seen, like int, integers, and floating point numbers, and booleans. There are others that we haven't seen, like strings and complex numbers. And we've just defined our own. And our own type that we've just defined has exactly the same kind of level or footing as all of the other types defined in Julia. There's nothing special about the ones that come predefined in Julia. But walker2d is also something else. It's also the name of some functions. So if we do methods of this same name, walker2d, we see that there are 2 functions with that name, right? So this is something special in Julia. We have an object and we have functions with the same name that are literally, or if you like, you can think of this object behaves as if it were a function. You can think of it like that. There are two options. Either I can pass in two integers or I can pass in two things of any type in principle. And so there's two methods for this, this object, and these are called constructor functions because they're going to be what we use to make an object of that type. So how do we do that? We call the function with that name as if it were a function with parentheses, and we pass in the parameters that we want to store inside the object. When I do that, then the question is, and I've assigned it to a variable w. What is w? Oh, it's an object of this type, right? And if I use, if I say what is type of w, then it tells me that it's a Walker 2D. Okay, so the point is that now I can really talk about, or I can really say, what is w? And I can answer the question. It is an object of type Walker. In other words, it is a random Walker. Right? Okay, so great. So it has some information inside, which are these positions 1 and 2. And I can access the information with w.x and w.y. So that means the value of the variable x that lives inside the object w and the value of the variable y that lives inside the object w. So we could create another Walker by calling the same function again with different positions, 3 and 4. And now w2 has its own copies of those variables. So it's like we have, one box that was called w1, or one bag that was called w1. And here's w1. w1, and here's, w2. And they both have their x and y inside. Okay. So x and y. Oh, it's so difficult to write with the mouse. Okay, so let's verify that actually w, the one we originally created, is still the same, and it is, right? So we really have independent copies of the x and y that live inside w and that live inside w2. Okay, so by the way, since this behaves just like a standard function, I could just create another method for it if I want. So if I want to be able to make an object of this type that by default lives at 0, 0, I could do that. I just make a method of this function, which takes no parameters and uses this other one that already, or other version that already exists like this. And then I can just call that function, call that new method, and it will create a Walker that's located at 0, 0. So this is a very standard thing to do in Julia. You can have a lot of different constructors, and you can see that we usually define them outside the definition of the type itself. It's also possible to have constructors that you define inside the definition. Those are called inner constructors, and they're useful when you have some restriction that you want to impose. For example, if I wanted these to be both positive, I would have to put that. If I wanted to force that to be true, that I could not create an object where they were not positive, then I would put that inside, and that would be called an inner constructor.
Yeah, speaking of constructors, someone was wondering about the untyped constructor method when you showed the methods and what.
Oh yeah. Thanks. Good question. Yeah. So what happens if I do this? Walker 1.0 and 2.0. What's it going to do? So then it will. So I can ask it, which method are you going to call? And it will tell me it's going to call this one, which does not have the type annotations, because these are not of the correct type, right? So let's look at methods again. You can see that we have this one that has these type annotations. That means that this version of the function is going to be called only when x is of type int64 and y is of type int64. In this case, these are floating point numbers. They're not of those types, and so it cannot call that version of the function. It has to call this other version. It knows that there are 2 arguments, so it will call this, right? If I try calling it with 3 arguments, then it'll just fail because there's none of the methods accept 3 arguments. I could make a method myself that did that if I wanted, but here there's a method with 2 arguments with no type annotations, and so it matches with this one. That means that it accepts things of any type. And so here it's floating point numbers. And so what do we want it to do? It doesn't really make sense, right? So let's see what it actually does when we call that function. What should it do? Well, what it does is tries to convert these values into the correct values, the correct types for the fields of this object, which are integers. And so it converts these into integers. Great. And what happens if I do 1.1 and 2.2? It tries to convert those to integers and then it fails. It cannot convert 1.1 into an integer. And so it will give you an error, which is called an inexact error. That's when you're trying to convert a number that cannot be made into an integer. Right? If you actually want to force it to be an integer, you need to use a special function, like, for example, round. So round to an integer, the value 1.1 gives you the integer 1. But by default, it won't do that. It tries to convert directly, and it can only convert directly without any special behavior like rounding if it's exactly already equal to an integer. Okay, hopefully that answers the question. Thanks, good question. Okay, so now let's make the walkers move. Otherwise, there's no point in having a walker, right? Okay, so we should just, it should be easy to make this thing move, right? We have this object W. So now let's just move it to position 10, move the X coordinate to position 10. And we get an error. Oh dear. So, sorry, I just need to get some more water. Be back in 1 minute. Okay, so what's going on here? So we are not allowed to modify the arguments. It says, and it's an immutable struct. So the word immutable means that literally we cannot mutate or change the values of the fields inside this object. So that seems like a bad idea if we want to have a walker that can move around, that can change its position. But actually in Julia, it's very common to use these immutable objects because it's usually will give you much better performance, will be faster, because it turns out that it's to do with where are these objects actually stored in memory. So I don't really want to get into the details of that, but basically immutable structs are usually stored on the stack, and mutable structs that we'll briefly touch on are stored on the heap. And the stack is basically much faster, has much faster access, and yeah, let's not get into the details right now. But basically, the rule of thumb is we should use immutable structs whenever we can in Julia. So then, in that case, how are we going to get this to move? And so the idea is to make it move, we're going to create a new object with the new position. Just create a new version, a new copy of this object. And so that sounds like a terrible idea. It sounds like it's going to be very inefficient. But because it's an immutable struct, Julia often knows how to do this in a very efficient way. In fact, this object might not even exist in memory. It might just be in like in main memory. It might be in the CPU's registers. That's the best case. That's when it's going to be really fast. And in that case, it knows how to modify this object without really creating a new object. So in fact, these objects that we're creating are sort of, they're only really for us. If you look at the code that Julia is generating, you never actually should see those objects existing. Okay, so here's an exercise. So take a walker 2D as an argument and make a function move right that just makes, that moves it to the right. So it takes in the current walker 2D and it returns a new one with a new position. And then make a function jump that makes it jump randomly, just like we did in the previous session, the previous notebook. But in this case, we're going to choose either the X or Y coordinate at random and move that coordinate by 1 step. Not like last time we moved both coordinates at the same time. Let's just move 1. Okay. So give you a couple of minutes to do that. And I'll check some questions in the meantime.
Yeah, people are a little bit wondering about kind of creating a generic walker versus this specific 2D implementation.
Yeah.
How would you approach creating this for any number of dimensions?
Yeah, well, great question. Yeah. Okay, so I don't think I think I decided not to go into that in the end, but that is a great question. So I'll maybe, can we come back to that a bit later? Can you remind me? And the next notebook actually is when we can talk about that.
Yep. And then another kind of question that's come up is kind of how are structs used in Julia versus other language? Can you have structs of structs? Can you put methods?
Yeah, you can do whatever you want. Yeah, I'm sorry.
And then also, like, can you put methods inside structs and like
yeah, so that is the $1 million question. Can you put methods inside structs? The answer is no. So that is the one of the main ways in which Julia is different from other languages, and I would go so far as to say better than other languages. This is a very different choice of the way you program compared to object-oriented languages. So Julia is not object-oriented in the same way that other languages are, because the methods, the functions live outside the objects. And that actually makes everything so much cleaner, so much nicer to work with. So that's what we're going to see a bit later in this notebook, like almost in 2 minutes. Okay, so let's let's do these. So I'm going to do move right of W, which is a Walker 2D, which is of type Walker 2D, right? And what we're going to do is going to return a Walker 2D. I'm going to take the X component of the Walker that I had passed in and add 1 to it, and then return the Y component. And I'm going to put those in a new Walker 2D object. And that's what I'm going to return from this function. Note that I could have written this without this annotation Walker 2D. That's also fine, but it means that any other type of object that I will pass in, it will try and extract its X component, try and extract its Y component, and then make a new Walker 2D object. So this is not a particularly good idea in this particular case, right? It makes sense to restrict it to Walker 2D in this particular case. So again, so the notation, the syntax, colon, Walker 2D means that we are restricting the function, the method, this method of the move right function to work only when the object being passed in is of type Walker 2D. That's what the syntax means, it's colon. This is saying, if I'm being called with this Walker 2D object, then do this, right? I could then make another function, another version of the function that worked for other types of objects in a different way. Right? In particular, this is not going to work for a 1D walker, right? So if I have a 1D walker, which I'll do in a minute, then I would want a different version of this move right function that worked only on Walker 1D objects. That is how we're going to use types to control the behavior that we want. Okay. Okay, so then how do we update our walker, right? So I'm starting with a walker, right? Walker, well, here, I'm starting with a Walker 2D located at 1, 2. And now I'm moving it right. But when I move it right, that just returns a new object. Sorry, just move right of W. That just returns the new object, but it does not change W at all. I can't modify the internal, like innards. You can think of it as the internal organs of this Walker object. I can't modify those. So what am I going to do? I'm going to set W equals this, the result of moving W. Right? If I do that, then I've changed W. But I changed it by reconstructing a whole new object and making W, this name W, sort of point to this new object, refer to this new object. So we talk about binding. So W is a binding to this new object. So this is, one way that you could think, one way that you could do this, one way that you could think about it. At the very end of the notebook, I talk about mutable structs, which allow you to modify the internal organs, allow you to change the values inside. So I personally find that a bit more intuitive when you are allowed to change the objects inside. But as I said, yeah, but this is you could think of this as a more sort of functional programming kind of approach where, so when you're allowed to change the values inside, we talk about having state in computer science. They talk about things being stateful. It has sort of internal structure that determines how it behaves. In this case, we don't really have that in the same way. We're just saying, if I pass you in this kind of object, give me back that other kind of object. And you don't change anything depending on the current state of your being, basically. Okay. So this is what we're going to do. We're going to have these functions on these immutable structs that return new copies of the new objects of that type. And we're just going to update the variable to point to that new copy. And as I said, this feels, if you come from some of the languages, this feels very wrong. It feels like it's going to be very inefficient. But in Julia, it will be efficient, fast. Okay. So now here's a version of walk that does that uses that idea. Oh no, sorry, that doesn't. This is the version that the previous version from the previous notebook. Now we're going to change it so that we have these objects and we're going to manipulate the objects. And that's this version, right? So I added a parameter W. So I need to first create a walker W of whichever type I'm interested in, and then make it walk like this. And so the code is almost the same, except now I'm moving, I'm going to have this move function that is going to accept this walker and return a new version of that walker. Okay. So now there's an exercise. Okay, so what kind of objects can we use inside this walk object with this walk function? So we can actually use integers, right? So basically the question is, what do I need a walker to be able to do? And if I look at this function, I can see what I need it to be able to do. I need it to be able to move. That's all. That's the only thing I do with my walker. And so if I define a function move on an object, then I will be able to use that object as a walker. And so let's do that. So in particular, we can try doing that for an integer, right? So you don't usually think of an integer as being a random walker, but we're just thinking of the random walker as having a position, and the position is going to be an integer. So let's do the simplest possible thing. We're going to move an integer by just adding 1 to it, like this. Note that I used this word integer, which is different from int64, which we've been using until now. Int64 is a concrete type, which represents a particular kind of integer stored in 64 bits. Integer is an abstract type that represents all integers, all things that behave like integers. So in particular, big ints like arbitrary precision integers, int 32, 32-bit integers, etc. Okay, so I can actually think of an integer as a random walker by defining this move object. Of course, it won't actually be random if I don't have any randomness, but that doesn't matter. And now I can actually walk down the integers just using my same function, right? So this is an example of generic programming again. So I'm going to start at x0, initial position 3. I'm going to have a length 10 trajectory, and I'm going to call this trajectory function. And it's just going to use the integers and walk along the integers using this move function that I defined on integers. But now, what I'm going to ask you to do is define a walker 1D type and a new method for the move function, and then use that to plot trajectories, and then use the walker 2D type that we defined and make its move function and plot trajectories. And then you can try and do that for a cloud of walkers as well, so n walkers in 2 dimensions. So just take a couple of minutes to do that. And then maybe we'll take a break.
Awesome. We're getting some questions kind of about what, with Julia structs, the immutable kind, if we put mutable things in them, how does that affect their performance?
Yeah.
And utility?
Good question. Yeah, so we're going to do that in some future notebook. Yeah, so you can put the words become annoying to pronounce. You can put mutable, so changeable object inside immutable, so unchangeable object. You can do that. And how will that affect the performance? So it will, So I believe that's a good question, and I don't exactly apparently know the answer off the top of my head. I have conflicting ideas in my head. They're coming from different, maybe, does anybody else on the call want to answer that? Chris, you there? Okay, yeah, so basically, I'm just thinking about, for example, if I have a vector of these immutable objects, then normally they can be stored just one after the other in memory. And I think that's still going to be the case. So for example, I'm thinking about the case where I have a vector inside my struct, right? So for example, if I have a struct hello, and it has v, which is a vector of integers. And it has, I don't know, some length or whatever, n, which is an integer, and then v, which is a vector of integers. So that is a mutable thing, and it's inside an immutable struct. That is perfectly acceptable. I can do that. And then I would make an object of type hello by doing something like 1 and the vector 3, 4. And so the question is, where do the things get stored? And the answer is this vector is not stored inside the object. What is stored inside the hello object is some kind of pointer that points to some other piece of memory where that vector is stored. And so in that sense, so basically this is immutable in the sense that I cannot modify h.v to point to some other vector. I cannot do that. I'm trying to change, where does this thing point to in memory? But what I can do is say, oh, h.v is a vector, so I can modify its second entry. Or I can even push to it. And now h dot, what is h? I actually changed what's inside h, but I didn't change, it's still somehow pointing to the same vector object in memory. And so, but I believe that this is still going to be efficient. Yeah. So what is not efficient is, if you, it's still going to be efficient because there's nothing being, basically nothing being allocated, right? If I actually made a new vector, then I would be allocating new memory. So basically, efficiency often boils down to avoiding allocating memory. That's sort of the slow thing that kills you in terms of performance. Okay, so let's quickly do this. So we're going to make a Walker 1D type. So it's just going to have a single integer inside. And then we're going to make a move function of that Walker 1D. So we're going to make a method of move that works only for Walker 1D. And what it does is it adds 1 to its x coordinate and then makes a new Walker 1D out of it. Right? And so now I can actually call my walk function. I can pass, so first of all, I need to make a Walker 1D object. Let's say it starts at 10. And then I'm going to make a walk. I'm going to call my walk function on that Walker object and make it move 5 steps. And so what it will return is a vector with the initial condition and then 5 steps after that. And we can see that it indeed is moving to the right. Right? And we can do the same thing if we make a Walker 2D object. I'm just going to say, I'm just going to use this move right function that I already wrote. And now I'm going to walk my Walker 2G. So let's make W2 to be a Walker 2D object that starts at, I don't know, 6, 7. And now I'm going to move my Walker 2D object 5 steps and, walk. And that's going to call the version. Okay, so this is the point, right? It's going to call the version of move that is specific to this type of object, W2, right? So it knows that W2 is a Walker 2D object. And so it has to call the version of move that corresponds to that. So if I do @code warn type walk W2 5, it knows that what it's getting in is a Walker 2D object. So it's a bit difficult to read, but it knows that what it's getting in is a Walker 2D object. This is the sort of very much lower level Julia code that it's generating. And you can see that at each point in this function, it knows exactly what type of object it's dealing with at each step. If you ever get red coming out, by the way, in code warn type, that is bad news. That's meaning that it cannot infer what type everything is. And then you're going to have a performance penalty because of that. And you need to fix that by trying to work out how to make it be able to infer what everything is, what type everything is. Okay. So hopefully that's clear. So let's just go over that again. So let's go back to the definition of the walk function with the new version. So I'm passing in this object W. I'm not saying what type W is again, right? I don't talk about types here at all. But Julia will work out what type W is. I mean, it knows what type W is. It has a type. And so, for example, here it will create an array of objects of that type only. This array trajectory will only be able to store objects of that same type. And then what does it do? It calls move on W. So what is it going to do? It's actually going to look up which version of the function move it needs to call. This is the key point, right? This is what's called dispatch. What is dispatch? It's just choose the correct version of this function to call depending on the type of W. So this is where Julia is different from, almost all other languages. So what Julia will actually do is compile a specialized version of this walk function for walker 1D type, for the integer type, for the walker 2D type. They will each get specialized compiled versions that are as efficient as they can be, as fast as they can be. And it's just amazing the way it does that. Yeah, and that's what leads to Julia basically to the fact that you can get this great performance from Julia, even though we never talk about types here, right? In most languages, to get performance, you would need to give everything a type so that it could compile to the correct version of the code. But what Julia is doing that work for you. It automatically infers, works out what all the types are for you, so that you don't have to, firstly, so you don't have to give types, but secondly, so that you can actually write code that works with different types and still is performant, has high performance. So that's the point. So the point is here, it's actually looking up once, which is when it compiles the code, it looks up once which version of the function does it need to call. In other languages, non-compiled languages, well, I guess I'm going to mention one specific language. In Python, for example, because it's interpreted, what it would do is at each point, at each step, every time you loop through this function, it has to say, what type is W? Oh, it's a walker 2D. Oh, in that case, I need to go and look up which version of move I need to call for a walker 2D. Oh, here it is. And it does that at every step. And that's one of the things that makes Python slow. Whereas Julia is looking that up once, is compiling a special version that works for that type. Okay, so hopefully that was clear. This is like the key point of the workshop, really. Key point of Julia, really. So actually, okay, and then the point about Julia is that you have multiple dispatch. What does that mean? It means that if I had some other parameter here in the move function, this was the number of moves you were doing or something, it would actually look up which version of the function it would need based on the types of all of the arguments. This is where the multiple comes in. So dispatch is choosing the version of a method of the function based on the type of the object, and multiple dispatches doing that based on the types of all of the objects that you're passing in. Okay, great. Right, so if we just look now at, we've defined these different types of move objects, move methods. So if we just look at methods of move, we see that indeed there are 3 different methods. And as I said, Julia will choose which one it needs to call depending on the type that it is managing to infer of the object that you're passing in. And there is a way of looking up, to see which version of the function it's actually calling, so to see the specialized versions of the functions that it has automatically created that it's kind of hiding from you. So the point is, the next time I call move, if I have my W, which is of type walker 1D, if I call move, the first time I call move on an object of that type, it will compile the specialized version of that function for that type. The next time I use it, and so you might see a delay. You might see a delay before it responds because it's compiling it for the first time. But the next time I call it, it'll be instantaneous. Okay. Good. So here's another exercise you can do that I'll skip over right now. And the way if you want to do this mutable version, you can do it by just writing the word mutable in front of struct, and then you can modify the value of x inside, but you'll lose some performance in general. And then when we do that, usually we'll put a bang or exclamation mark at the end of the function name to emphasize that we are updating, modifying the variable. So I think we're going to leave that for now. Let's take a 5-minute break, and we'll carry on. Thanks. Okay, are there any questions that we should cover?
There was a question about jump and whether to manipulate the X or Y.
Oh, yeah. So I was just saying that you should choose randomly either X or Y and then manipulate that one. That's what, I mean, you can do whatever you like, but that's what I wanted you to do.
And then there's kind of a question: if you pass a function to a function, how does that affect the type of the output and kind of the type stability?
Okay, yeah, good question. So yeah, if you pass a function into a function, how does that affect type stability? So type stability is this idea that you want to be able to determine the type of everything in the function. So yeah, that's a good question. So basically Julia just sort of follows everything through, right? So if I do f of x equals 2 times g of x,
Right, so inside the function f, I'm calling this function g. Well, okay, that's not quite what you wanted. You wanted me to actually pass in g. So let's pass in g as a function to f, as an argument to f, sorry. And so now, so let's say that I'm going to define a function h, which is x plus 10, right? So, okay, I can't define h because I already used it for something else. K of x is that, right? So I'm going to pass in the function k to f and the value 3. What happens? So I'm passing in k. So there is a debugger in Julia that you can use, for example, within Juno and probably VS Code now. I don't know. People will be talking about that later. But I'm not going to use that in this tutorial. But you could go through and use the debugger to work out what was going on. So what does f do? So I'm passing in k as, so g is going to be k, right? And then x is going to be 3. So it does 2 times g of x, which is 3. So it does 2 times g of 3, and g, I'm saying, is being replaced by k. So basically what it's doing is internally is saying, oh, I have, it's basically just doing g equals k, you can think of, right? So the point is that if I now use g, I'm actually using k, because g is just another name for k. It's like 2 names pointing to the same object. It's sort of an alias, another name for the same thing. So I'm effectively doing 2 times k of 3. And k, what does k do? Oh, it does this x plus 10, right? So 3 plus 10 is 13, and then I'm multiplying it by 2, gives me 26. And so how does this affect type stability? Well, I'm passing in, Julia knows which function I'm passing in, and it knows which type I'm passing in. So it knows, well, when I call k of 3, it knows what's going on with types inside k. And it knows that k returns an integer 64 in 64. And so it knows that the result of this calling k of x is an n64. And so it knows that it's doing 2 times n64. And so if I do @code1 type of f of k and 3, you can see that it knows exactly what to do. And it knows that everything is an n64. So it just propagates through all of the functions that you're passing in. And it comes out with knowing that you want an n64. If I have another function, let's call it k2, which instead of doing x plus 10, did x plus 10.0. If I now do @code1 type, so if I now do f of k2 and 3, it knows that the result, it propagates this fact, it starts with an integer, but because I'm adding a float to it, it converts everything to floats. So it ends up with a float. But now if I do @code1 type of f of k2 and 3, it knows that. It just propagates the information all the way through each function. So as long as it's able to, as long as each function in the sort of complicated thing that you constructed is type stable, in other words, given an input type produces a certain output type only, as long as that's the case, then Julia will be able to work out what's going on, and everything will be completely efficient and probably is inlining as well. So it'll be very fast. Yeah,
awesome. And then as a follow-up to that, is there any way when you're expecting kind of a function to be passed into a function to kind of put any parameters on that in terms of what that type?
Yeah, that's a good question. So that is a very good question. Yeah, so for example, you only want to be able to pass in a function that takes an integer and returns an integer or something. So in general, that is not possible in Julia, because in general, a function can have different methods that have a different number of arguments and return different things even. So in general, it's not possible to do that, but there is a package called, this is like very technical. I'm using these square brackets for technical comments. And so this is like super technical. The function wrappers package enables you to specify input and output types of functions for type stability. So if you really need that, then you can use this function wrappers package, but you probably don't need it. But yes, in general, it's sort of difficult to restrict things in that way, to restrict only to certain types of functions. But you don't really need to either. You can just write it in accepting any kind of function, and then if that function doesn't behave in the right way, it'll just throw an error, right? If it doesn't have the right number of arguments or it doesn't return the right type of thing, it'll just error, and that's fine. Okay, great.
So, so there was this little exercise that I've lost track of. Which exercise were we doing? Yeah, I think we'll just leave it there. Or is it, was there another question with the exercise? Well, I've forgotten what the question was that you asked about the exercise. Anyway, I think we should move on. Okay. So let's move to the next notebook. Types for agents. Okay, so remember this model that I know we're getting lost in a lot of detail of types, but it's very important. So now we're going to come back up and think about what we're trying to do. So what we're trying to do is write this agent-based model or individual-based model where we're tracking individual people or animals or things that have an infection, and they're moving around. And then when they sort of collide with each other, we want to transmit the infection with a certain probability. So we need an agent type, right? Because that agent type is going to have a position and it's going to have a number, it's going to have something that tells us whether it's infected or whether it's not been infected yet, which is called being susceptible. So whether it's susceptible or infectious, let's say, whether it's going to transmit the infection, that means, or whether it's recovered or removed. So whether it's either recovered from the disease or unfortunately died. So we need to represent that inside an object. So we want an object, right? We want to be able to say, oh yeah, that object is in this position and has that particular infection status. So of course we can represent this status using a number like 0, 1, or 2. But then our code is going to have these sort of numbers all over the place, right? I'm going to be checking if this one is 0 and that one is 1, then do something. And it's going to be totally unreadable because I can't ever remember which number is which thing, which status. So we don't want to do that. We want to use variables, names, right? So we want to use the symbols S, I, and R inside my code. So we could make these global constants. And that's effectively what we're going to do, but we're going to do it by using something called an enum. So enum means enumerated type. So we want to define a new type, which is infection status. And it can take the value S, the value I, or the value R. And those are the only values that they can take, right? And so we can do this with this macro at enum. We give the name of the type, and then we give the names of these objects that we want inside. Sorry, the names of the names of these objects that we want to well, the names that we want to be able to use that are types of infection status. Okay, so if I do that, then what is infection status? It's just the name of a type. But inside, we know that somehow the only values that it can take are S, I, or R, and those correspond to the values, the numerical values 1, 2, and 3. In our particular case, we don't care about those numerical values. In other applications, you might want special numerical values there. You can specify those with more equal signs in the definition of the enum. So what is the point of this? So the point is, if I have an infection status, a variable of type infection status that lives inside an object, for example, then if I then it will not be able to take any value except S, I, or R. That's the point. Okay, so and we can check that. So if we have a variable of one of these types, like I, so if I just type status, it'll tell me, oh, its value is I, which is of type infection status, and it has a numerical correspondence 2. And the point is we can actually check the status with this double equals, which is checking equality in Julia, if this variable is equal to this value I, right? So we can use I instead of 2. We can also use 2. That also, it allows us to do that. So let's say 3 is recovered, and it will fail in this particular case, right? So is status equal to 2 in this case? Yes, it is, because, sorry, what? No, it's not. Oh, I thought that would work. Apparently it doesn't work. Okay, good. You can only use I. Okay, but you can actually convert it to an integer if you want. Int of status works, and then I can check if that is equal to 2. But of course, that's defeating the point. The point is I want to be able to use I to check I want to be able to use the thing that's going to make my code easier to read.
Okay.
David, a couple quick questions on
Yeah.
enums.
Right.
Are the values for the enums just automatically inferred, and is it ordered?
I just, because I said to start at 1, it started at 1 and then just added 1 for each subsequent value. But you can specify whichever integer values you want here, like -10. You could do that. If you don't specify the value with an equals, it'll just sort of assume that you're starting at the one you specified and then it's adding 1 each time. Yeah.
And then you could compare like S is less than I. Would that
Good
make
question.
sense or no?
I mean, I don't actually, yeah, so I think you can. Yes, you can. Okay. Yeah. But, usually the answer to that kind of question is don't ask me, ask Julia, right? Does this even, if you're not allowed to, in quotes, then it'll just give you an error. In this case, you are allowed to, and it works. And it uses that ordering, uses those numerical values. Yeah. And so that's useful for some. I actually used that for a particular application in interval arithmetic, which is these packages I've been working on. I forgot to introduce myself at the beginning of the workshop. But anyway, yeah. So I'll be giving another workshop on Monday on interval arithmetic, which is a set of packages that I've been working on for a few years with a colleague, which enable you to get guaranteed numerical results on for calculations. Okay, so we want to define our agent type. So the simplest way to do that would be this, right? I want an immutable struct, which has its position in 2 dimensions. We're going to suppose it's in 2 dimensions for the moment. X and Y, which are both integers in 64. You can just use int. Problem with just int is that on a 32-bit machine, and there are fewer and fewer of those around, I guess, or maybe Raspberry Pis still, that'll be an int 32. So it's just better to actually specify which one you mean. Maybe is better. Okay, and then a status which is of this type, infection status. Okay, so I forgot to say, as in the exercise, so firstly, create an object of this type. And then make it move. Okay, that's the exercise, please. Okay, there was a question, how do you make an object of this enum type from an integer? So that's a good question. You can do this. Infection status of 2, you can use it, infection status, as if it were a function, and then it will give you the one that corresponds to that value. And if you try and use an integer that's outside the range, it'll give you an error. Yeah. Thanks for the question. Okay, so let's do this exercise. So how do I create an object of this type? Of course, I use the constructor, right? So let's look at the constructors. As usual, we expect to have 2 constructors, one where you give all of the types and one where you give where it tries to convert to the right types. So how do I construct an object of this type? I give it 2 integers and an infection status, S. And that works. If I give it a number instead of S, it does not work. It does not know how to convert an object of type int to an object of type infection status. So you do have to just specify S, or you could do what we just saw and put infection status of 1. That would work. Okay, so that's how you make an object of this type. Now I want to make my move function that takes a walker, or let's say an agent A, which is of type simple agent 1. So I'm calling it simple agent 1 because there'll be several iterations of the design of this structure. And the struct
And it turns out that in Julia, you cannot redefine a struct. Once you've defined it, once you've specified like the shape of it, the template, you cannot actually change it. So that's why I'm calling it simple agent 1. So how do I move a simple agent? So you can choose any of the versions of moving that we've done already. So for example, I'm going to move its x coordinate by 1 and leave its y coordinate fixed for simplicity. And then I need to keep its infection status, right? What did I call it? Status? Yeah. And I need to generate a new agent type out of that. Agent object, or a new object of this type. So because this is a nice simple function, again, I could just write that all in one line, right? So that's how I'm going to move my agent. I'm going to change its x position, but not its y position in this particular case. And I'm going to extract its current status and put it back in the new version, right? So how could I write a function infect of this simple agent? Well, I would leave its position alone and return that it was infected, I guess. So again, if I have my agent, so let me call this something. I'm going to call this A equals this agent, right? I'll just copy and paste that. So if I have A, which is an object of this type, again, suppose I infect A. What does that do? It gives me a new agent object, but it does not modify A, right? Because A is not modifiable. Again, what I would actually have to do is sort of update the binding of A. A equals infect of A, and then that's effectively that's how I'm going to infect my object. Okay, but the problem with this code is that it looks almost the same. Oh, I've just realized that as an issue. Okay, oh dear. Yeah, it's a bit more complicated than I thought. So there's an issue here, which is that this code is almost exactly the same as the code that we had for moving a random walker in 2D, for moving a simple walker in 2D. So we're actually duplicating the code here. And so what I was going to say is that a solution to this would be to use inheritance. And so what does that mean? It means I can say, oh, a simple walker 2D, which just has an X and Y, and a simple agent, they're both going to be subtypes of some other type. They're both going to be, you can think of that as being a kind of abstract walker 2D. So abstract walker 2D is going to be an abstract type. I define that like this, with the keyword abstract type end. That literally makes a type that's completely abstract. That means I cannot make an object of that type. It's impossible. If I try and make abstract walker with parentheses, so 2D, abstract walker 2D with parentheses, it says there are no constructors. So there's no way of making an object of this type. Okay, but I'm just using it as a label to say, oh, a simple walker 2D and a simple agent are actually kind of have something in common. What do they have in common? Well, it turns out they have the fact that they have a position in common. And so what I would want to be able to do is write a move function. And yeah. And so the exercise is not actually really correct. So it says, can you extend the move function so that it works for both? So I want to just write one method that works for both simple walker 2D and simple agent. And so that was because I was thinking about mutable structs. If they're mutable, then all I want to do is change X and Y inside the object. And I can do that in the same way for simple walker 2D and for simple agent too. So for mutable objects, I can Yeah, okay, what I just said. I won't write it out. So this is actually not going to work so well. So there is a way around it, but I don't really want to talk about that right now. So maybe get me to talk about it in a few minutes. There is a way that we could write a function move. Yeah, I think there's a way we can write a function move that's generic that works for both of these two types. But actually, this is not really the right way to do it. So let's just skip to the right way to do it. So the right way to do it is called composition. So this is usually more powerful and general than inheritance. Okay, so what we're going to do is actually put the object inside another object, right? So so what is an agent? Instead of having the position be an x coordinate and a y coordinate that live inside the agent type, I'm going to put a walker 2D object inside the agent type. So this seems a bit weird because I'm saying an agent contains a random walker, but that's not really what I'm saying. I'm just saying it contains a package of useful information, which is a position that I'm going to think of as a single object, right? This is a way of getting more abstraction. Okay, so when we do that, so I forgot to evaluate the code where I define simple walker 2D. Let's just put that back. So when I define that, everything seems to be working. So now I'm going to treat the position of the agent as, this type where I'm supposed to have already defined its behavior. So because we're in a new notebook, you'll actually have to redefine the move method for simple walker 2D. So you can just make it move to the right for the moment. And then do the same for agent. So I want you to work out how to actually build an object, construct an object of type agent1, and then how would you extend move for that function? Please. Yeah, so there's a question. Is it easy to change only one thing inside an object? So change only one field inside an object. There is a package called setfield.jl. I think there are various packages, but that's the one that I remember. Setfield.jl can create a new object with only one thing changed inside. And there's another one which is lens.jl, I think. So it's quite possible that when you have a complicated object and you just want to change one thing inside, maybe that's when you can start thinking about using a mutable struct instead of an immutable struct. Okay, so let's just remember how we define move for a simple walker 2D. We give it back a new simple walker 2D where we took the x coordinate and added 1 and kept the y coordinate. Now I want to define move for this agent 1. So first of all, I want to know, how do I actually construct an agent 1? Well, so first of all, I need a simple walker. So let's put that a 1, 2. And now I want the agent. I'm actually going to pass in this simple walker object and a status S. And that will construct an agent 1 that inside has a simple walker 2D. So of course I could have just written all of this myself, but it just becomes annoying to read, when and confusing how many parentheses do I need. It's much better to just sort of split up the steps. First of all, I construct the walker, then I put it inside the agent. There's also a way to print out your types. You're going to start having these complicated types and they're going to be very unreadable. So there's a way to extend the base.show function to make them prettier. So I guess we should just quickly do that. So base.show of, you need this IO object to start with, and then, which just means input output, and then you do A, which is of type agent1, and I'm gonna, so function, this is a method of that function, and I'm gonna do print to IO sort of agent object with position w.a and status a.w, I mean, and status a.status. So this dollars or dollar symbol means string interpolation. So it's going to put the value of this object inside the string, right? So there's quotes. We haven't really seen strings. I don't use strings that much. So that's why you don't use strings that much in scientific computing, which is what I do. And so now if I look at my agent, sorry, that's not right. It's called position, not W. So now it prints this out in a nicer way, right? And then I could also do the same for simple walker. So let's make simple walker look nicer. So I'm going to say just print it out as a tuple instead of with the word simple walker. So so let's call this w.x, w.y. Simple walker 2D, sorry. And now, oh! So the kernel just died. That's bad. So let me just reevaluate some of these things. Why did it die? What did I do wrong? Our infection state is not defined. Let me just make it an int. There we go. Don't know why it didn't work last time. Okay. Yeah, so now we can just print it out in a nicer way. Great. Okay. So now we get to a really important topic. So we don't have that much time left, but this is a really important topic. So and I think this covers some of the questions that people have been asking, which is, okay, I want an agent. So far we've had an agent that lives in 2D, right? We explicitly said that inside agent, it had a position which had to be of type simple walker 2D. So it only can live in 2D. But actually, an agent might live somewhere else, right? Again, just like we had before, we were thinking about walkers moving in different dimensions. This agent can also maybe just live on a line, or it could live on a network. So I actually don't want to restrict it to only being simple walker 2D. I want to be able to put any kind of, spatial type in there. So how could I do that? So one way that you might think of would be this. So I just leave out the type annotation, and I say, struct agent2, it has some kind of position, and I'm not going to specify what type it is. So then I could put whatever type I want inside, right? I could put an integer inside with an infection status, and that will work. I can also, by the way, put a string inside, which you probably don't want, right? So this is not actually a good idea necessarily, because this will allow anything, any type to be stored inside there. And by the way, this will also lead to very bad performance. So you should almost never make an object with an untyped argument. So what should we do instead? We should do this. So the solution is to use a parametrized type. What does that mean? It means I'm going to say, oh, position has a type P, right? But that P is actually going to be a parameterized type. So what does that mean? So it's, so I could think of doing something like the following: struct agent3 int _ int, so that I'm putting the type in the name, and then I'm going to have position, which is an int64, right? Or I could have struct agent3 float 64, and I could have the position be a float 64 instead. So you can see that what I'm doing here is basically doing the same thing over and over again, but just changing something, changing a parameter basically. And so there's some missing abstraction again here. How can I make these things look, how can I only write this thing once? And the answer is I would do agent3 with some type t inside, and then make position be of type t. The syntax for that is these curly braces. Some type t, right? So in fact, you can think of it as allow any type t. Sorry, 2 colons, position 2 colons t, agent 4, let's say. Right, so that is going to, so what happens now? If I construct and type an object of type agent 4, and I pass in an integer, it realizes that, okay, it's doing some kind of matching. It's matching, it sees that position is of type integer, so t must be an integer. That means that I've constructed an object of type agent 4 parameterized by int64. If I now construct one with a float inside, or let's say a string inside, then it will actually make the thing and parameterize it with a string. So Julia is doing the hard work that I did when I typed out these type names twice. Julia does it for me, right? Does all the work for me. So that's what the point is of a parameterized type. And so here is how I could do that with with my agent type. It's going to have a position, so I've called it the type P instead of T, just because P for position. But so P is the type parameter that goes inside these curly braces. And here I've also said, oh, I'm going to restrict that to only being of type abstract Walker. So you can do it unrestricted like this and allow any type P in there, or you can restrict it to be subtypes of this abstract type, abstract Walker. Okay.
Okay, but a quick question about type parameterization before you move on. People are asking, how does it kind of compare to what other languages call generics?
So I'm not, so this is sort of like a generics or this is basically the same as generics or templates in other languages, I believe. Yes, you have a type parameter and so I'm not too familiar with other languages like, I mean, the other language that I've used where you have some kind of generic programming is has these templates where you have type parameters, and it's very similar. Yeah, the idea is similar, but so I'm not sure if it's completely similar because so what Julia will do again is everything will be compiled in a special. So it's not similar in the sense that in other languages you often have to specify in advance what types you're allowed to put in here. In Julia, I can just go ahead and construct types with anything in there. Right? 3 and S, agent 5, hello and S, etc. So I can make an arbitrary number with anything in there, in fact. Right? I could put another agent in there, agent 5, 3 and S, comma S, and I can do that. It's not a very good idea, perhaps, but I can do it. Okay, so I've already done the exercise for you. So that's how you construct agents. And Julia, again, will work out which type parameter you have. And the point is, again, that now it's, so now the exercise is actually write a move function for this agent, right? So just take a couple of minutes to try and work out how you would write that move function. And then, and then we'll do walkers in n dimensions. So there was a question, how can you write, is there a way to make a generic walker? So I don't actually quite understand what you mean by make a generic walker.
I think this harkens back to kind of like a walker in any dimensions.
Yeah, okay, so we'll do that, yeah.
let's call this any number of dimensions. That is a very mathematician's way of saying it, n dimensions. N. Okay. So let's suppose, for simplicity, well, actually, no, let's use a simple walker 2D. So let's say that my agent is walking in 2D. So I'm going to use agent 5, which is this parameterized one with just any type parameter. It starts at 1, 2. I'm going to put a W in there, and it's going to be susceptible. And the question is, how can I make one of these things move? So A, which is of type agent 5, I am not going to specify anything about the type parameters. So agent 5, if I just do agent 5 without anything, it just tells me that it's agent 5. That's not very useful. Thought it would do something different. Okay, never mind. Basically, agent 5 refers to sort of any of these parameterized types. Right? So basically, it's an abstract type actually now, agent 5. And so this means for any, if I pass in, it means specify a method for this function, which will work if I pass in any object A of any subtype of this agent 5 type that I just defined. So how is that going to work? Well, it needs to create a new agent 5 object, and I'm going to move the walker, right, that lives inside the agent. And then I'm going to copy the agent's current status.
A.position.
Thanks. A.position. Yeah. So if I have my A and then I move it, we see that indeed it moved right. And so the point is that this works in general, right? This is generic code now. I'm not specifying where my agent lives. I've hidden all that information away inside the walker that's hidden inside the agent. And so now this code is going to work in any context for any agent that lives in any space, as long as that object that's describing its position knows how to move, right? So if I had a network, I would have a function move that had information about, the information about the network is stored inside this position object that I'm passing in, and it knows how to do this move on the network and then return a new position on the network. And that would all be hidden away inside, and the agent doesn't need to really know anything about it, right? So this is a way of it's like treating the position as a black box from the point of view of the agent. So we're building up a lot of complicated functionality piece by piece. Okay, so let's quickly look at walkers in any number of dimensions. So what I want is, how would I do struct simple walker with a parameter, which is the number of dimensions? And so I want n, which is the number of dimensions. And so what do I want inside here? So one of the things you could put is an n tuple. So position was going to be an n tuple of length n and some type t. So actually, I'm going to need a type t parameter as well. Okay, so now I can make simple walker of, and I'm going to have to pass in a tuple. So 1, 2. So there we go. That's a simple walker that lives in 2 dimensions. And now a simple walker that lives in 5 dimensions, I can do like this. And there is a simple walker that lives in 5 dimensions. So Julia has worked out, so n tuple is a tuple with n things inside, right? And Julia has worked out that what length it is, what type each one is, and it has put those in the type parameters of this object. So as I said, there's this static arrays package that makes using this stuff a bit easier. So I would make a different version, which instead of a tuple had an S vector, which means static vector. Static means that the size of the vector is known. So it's a type parameter. And now I do simple walker 2. How do I make a static vector? One way is with this special SA square bracket syntax, is like as if it were a kind of array. -1 to 5.0. That will actually convert automatically all of these to the same type. And then that's the type that it will use. So yeah.
So if this is W, then how can I move W? So if I look at W.position, that is a static vector. And now I can add another static vector to it. So for example, plus 1, 2, 3, it will give me a new static vector back, and then I can use that inside my move function. And so this is, and then the way that you can set change only one thing inside there. So if I call P W.position, that's the static vector, I can actually use set field. I think I should be able to use set field P10 2, and that will change. It's not called set field. What's it called? I've forgotten. Set something. Set index. Sorry, set index. Set index P10 2. That will change the second index to the value 10. So that answers the question about how you. That answers the question for static vectors about how you change only one entry. So it's creating a new object, changing just this one entry of the thing. And there's a similar function for tuples. Yeah. Okay, great. So 10 minutes left. Let's move to the last notebook. So the last notebook is just an extended exercise where you're actually going to write the simulation. So you should now have all of the tools to do that. Of course, I know that we've gone quite fast. We've covered quite a lot of material. So I'm not expecting you to necessarily be able to sit down and write this all, without. You should just go back and look, at your leisure at what we've covered, at the concepts we've covered. So let's just go over what the exercise consists of. So as I showed in the simulation, what we want is a box. And the point is that when walkers are at the edge of the box and they try and leave the box, then they can't leave the box, right? They're just going to stay where they are. That's the simplest thing you can do. So if it's here currently, that's like at the edge of the box, and it tries to jump in that direction, it just stays where it is. That's the simplest. I mean, there are various other rules you could use, of course, but that's the simplest rule that I can think of. And so we're going to make a new type, which is confined walker 2D. Confined meaning it's trapped inside this box. So what's it going to contain? It's going to contain a walker object and a box size. So we'll just assume for simplicity that the box is square, or, if you want to make it rectangular, you can have two different sizes for the box. And those are going to live inside this confined walker 2D type. And then, of course, we're going to extend move to confined walker 2D. So what's going to happen is you're going to call the move function for the walker 2D, and you have to check if it stepped outside the box, right? And if it did, then you'll just leave the walker where it is. And now we can make an agent using what we just saw, which has this confined walker 2D type inside, right? So the fact that we've now got this way of having this sort of parameterized agent type where we can put any kind of position object inside means that it's really easy to now switch from having an agent that can live anywhere in space and move around as it wants to having an agent that's stuck inside this box. And the point is that the code for the agent type, the code that refers to the agent type, so that does moving and then later on infecting, should not know anything about what kind of world it's actually moving in. All that information should be delegated down to its internal object that should contain all that information. That's one way of conceptualizing this world, right? So we basically are trying to sort of, isolate all the information at different levels. So all the information about the position should be dealt with by this object that lives inside agent. All the information about infections should be dealt with in the infection object, etc. So it's one approach. I'm not saying that this is always appropriate, but it's a good way to build up this kind of simulation. So I should just mention that there is a package in Julia called agents.jl with an agent with an S at the end, .jl, which is a very complete agent-based modeling package. Obviously, that's not what I wanted to do in this tutorial, and this tutorial was about learning about Julia's types. But if you want to actually write an agent-based model in Julia, that's a very good option. where you don't have to do all of this yourself because they've already done it for you, basically. Okay, so now we need to, so what are we going to do? So we have this agent type with this confined random walker inside. And now we want to, looking at this picture, we want a lot of them. We want n of them, 100, say, or 1,000 or 1,000,000, depending how big your computer is. So we're going to start them all off in some positions. Now, the rules of this model are going to be that we can only have one agent on each position, on each grid point at any one time, at most one. So either empty or one agent. That's just the simplest way that I could think of to make the simulation work, because basically, if you have several agents on top of each other, it's difficult to decide which one infects the other one. That's the only reason for that. But so the first thing we need to do is generate the initial positions. So we're going to have an initialize function where you're going to generate random positions and put the agent there as long as it's actually an unoccupied, currently unoccupied site. So you need a function check occupied that checks whether a particular position is occupied. So you might worry that this is going to be a bit inefficient. You're going to have to check through all of the agents that you've already put down to see where they are. And it is indeed inefficient. And there are ways that you can make it more efficient. So you should think about how you can make it more efficient. And then you're going to make them all be susceptible, except for one, which you choose to be infectious, right? That's this picture that we had. One is infectious. And then you should write a function to actually visualize this by drawing this box and drawing all the agents. Okay. And then, so that's this first part. Okay, and now we're going to do the dynamics. So in the dynamics, what we're going to do is at each step, we're going to choose at random one single agent, and we're going to move it. Well, we're going to try to move it. It's going to sort of propose a new position. It's going to say, I want to move here. I want to move to this next door site, right? So like this one is going to say, I want to move this way. And then in the next time step, this one is going to say, oh, I want to move that way. And so if the site where it's moving to is empty, then we're going to allow it to move. If the site where it's moving to is full, we're going to block it and say, you cannot move that way, but you might be able to transmit an infection. So if this one, which is infected, moves this way, then it can infect this one with probability pi, p sub I. And then at each step, just like we did at the start of the workshop, it's going to recover with probability p sub r. So I wrote out all those rules here. And so the point is that we're going to make a struct again, right? Like a simulation struct present the whole SIR simulation. So it's going to have the size of the box, the probability of infection, and the probability of recovery as fields, but it's also going to have this list vector of agents. So this is where we're putting this mutable object, which is a vector, inside the immutable struct. And it's perfectly fine to do that. And it's perfectly, it is very efficient to do this. Okay, so what are we going to do? We're going to do dynamics, which is taking steps, basically. So we're going to write a function called step. Because we're going to modify the vector of agents, we're going to use step bang to do that. So we're going to choose one of the agents and we're going to move it. Right? So we're going to change the agent that's stored at the vector. But we can't change inside the agent. We have to make a new agent and put it back inside the vector. Okay. Unless you make them mutable structs, that's also fine if you want to make your agents mutable structs. Okay, and then so you write that function and then you just run the dynamics. You just run the steps again and again and again. And so what we would like to do is make it basically what we're doing here is making a copy of the entire system. So basically the copy of where are the agents located, and we're also calculating the total number that are in state S, state I, and state R at each time step, and we're plotting them on a curve. So basically what we do here is we pre-generate the data. So we're going to run the whole simulation for some number of steps, say 1,000, 300 in this case. And we store all that data using deep copy in a vector. And then the manipulate will just, you should just write a function that visualizes one frame And then you should just put that visualization inside this manipulate object. And then you'll get this beautiful simulation and visualization of an epidemic model, epidemic spreading. Okay, so unfortunately, that's the end of the time. So this is a challenge exercise to write this simulation. I think it's a very, well worth to write the simulation, and it's, very relevant, unfortunately, in the moments that we're living. It's called the SIR model, and a spatial version of that, where these walkers are bumping around and moving around and bumping into each other and trying to transmit this infection, which is roughly what happens in reality. Of course, this is a very simplified model, and as I said, we taught this course last semester, which I linked to in the repository, and there we discuss in much more detail the mathematical modeling aspect, and is this a good model, or how do you improve it, or what about errors, etc. I mean, all that section, all of that part, I'm just ignoring for the purposes of this workshop, which was about learning Julia. Right? So let's just take a couple of minutes to summarize. So what have we done? So we started off looking at random walks. No, we didn't. We started off looking at just sort of remembering how to use for loops, arrays, generating some data and storing them in an array, and then plotting the result and using interact to get an interactive visualization as long as it works. And then we moved on to looking at random walks and model motion in space. But what we were interested in doing was trying to write code that didn't matter or was agnostic. It couldn't see what kind of random walker was moving around. And we saw that the best way to do that was by writing a new type, inventing our own composite type or aggregate type, or called a struct, inventing our new type with new behavior. So the behavior is given by these methods that are functions that act on those objects. And those methods live outside in the world, right? They do not live inside the type. The fact that they live outside in the world means that we can make them act, make different versions of the functions that can act on each different type. And then we can make generic code that doesn't talk about types at all, but knows, Julia will know which version of each function to call based on the type that you're passing it in. And then we saw that we can also parameterize the type to get even more even more generic code. In other words, code that works on even more possible types, but still does it in an efficient, fast way. Okay, so I think we'll finish there. Thanks so much for your. Okay, so there was one final question. Is it better regarding performance, is it better to have separate structs for 1, 2, and 3 and n dimensions, or just to have the n dimensional? So you can have, so it should be basically the same performance. If you write it correctly using, for example, static vectors, it should be, if you just write the code generically for n dimensions, it should be just as performant. It should just be as good performance as doing it separately for each one. So just do the generic one.
Thank you, David. This was a great introduction and a great way to start JuliaCon.
Thanks a lot for your help, Mary, and thanks everybody for your for attending. Hope it was helpful. If you have any questions, please let me know, and hope to see you at the rest of JuliaCon 2020. Okay, thanks a lot. Bye. Good day.